much for the very kind introduction. And good morning, esteemed colleagues and friends. It's a profound honor and privilege to stand before you today at ICRRHHE 2024 and fourth biannual meeting of Society of Radiation Research to deliver SRR-BB memorial lecture. So I learned that Dr. B.B. Sing's name resonates deeply within the global scientific community, particularly among those of us dedicated to the field of radiation research. It's my hope that this lecture serves as a tribute to his legacy and a reflection of his enduring influence on our field. So, I want to move to the talk. So today I would like to talk about the radiation and chromosomes. Chromosome is a very old-fashioned style analysis to examine the effect of radiation. But I'm still sticking to chromosome. I will explain it later. Okay, A bombing. So A bomb was dropped on Hiroshima and Nagasaki. It's 79 years ago. So that means next year is the 80th anniversary of A bombing. As you know, A bomb survivors suffered leukemia from 4 years after A bombing, especially children. They suffered a lot about leukemia. And then the incidence going up very quickly and it goes down very quickly again. And then recently, the incidence of myelodysplastic syndrome in elder person, it's related to leukemia, it's gradually increasing. And 10 years after the bombing, the incidence with thyroid cancer increased, and after that, breast cancer, lung cancer, GI tract cancer, skin cancer, and meningioma went up. This is a very known epidemiological study. One more important point is chromosome aberrations. Actually, I was a graduate student in Professor Kamada's lab. In this lab, we examined the chromosome from A bomb survivors. That's the reason why I'm very interested in the chromosome aberration and radiation. And as you see here, these arrows indicate the abnormal chromosome in this A bomb survivor. She suffered no leukemia, no cancer. That means this chromosome derived from the normal lymphocytes. But still, with these very complicated chromosome aberrations, she could have a normal life or close to normal life. And the important point is here, the x-axis shows the distance from the epicenter. So the people who suffered A bomb within 500 meters, almost all of them carry such kind of chromosome aberration, and the incidence goes down like this. So this shows that the chromosome, simply shows that the chromosome aberration can apply for the estimation of radiation dose. This is a very simplified history of radiation disaster, biology, and medicine. So as you know, A bombing is in 1945 here, and 3 Mile accident, 1979 here, Chernobyl here, 1986, JCO accident in Japan, this happened in 1999. The 2 workers died because of acute ARS, very severe ARS. They received more than 20 grade or something like that. And as you know, 2011, we had a Fukushima accident. Okay, so now it looks every 10 years we have a very big accident. But government can easily forget about it. Japanese government also. I don't know how about the other countries. Okay, then if you think about the radiology field, so CT was developed around 1970, and now we have a lot of CT around 2010. We are now going to the next generation CT. And also in the biology and medicine field, so the chromosome, so the number of human chromosomes was determined in 1954, and the Philadelphia chromosome in chronic lymphocytic leukemia was discovered in 1960. So the chromosome analysis has a very long history. And as you know, so the molecular biology techniques are developed around 1980. And I enjoyed my graduate student era around here. So it's some kind of just after introduction of molecular biology technique into the medical field. So I am very curious about how we can apply this molecular biological finding to the medical field, but I noticed that it's not a good way now. Now we notice it after examining, after studying so many things in molecular biology. I now go back to chromosome. It's because we could establish high throughput method to analyze human chromosome. But of course, the omics approach is very, very important to have the next generation biological dosimetry, and also did the finding obtained from the omics approach or some other approaches lead to the molecular target therapy, or it's in combination with ionized radiation. So now we are in the very interesting era from this map. And as I told you, the reason why I'm still sticking to the chromosome analysis is this is, you can say, it's a single cell whole genome analysis with a very, very low cost. And it has a very long history. That means we know what, because the chromosome analysis using Giemsa staining was established around 1965 or something like that. So we have a very long history and very huge amount of data about the chromosome aberrations. And also, from the biological point of view, chromosome abnormalities respond is double-strand breaks, not only double-strand break, stored fork and other DNA damage, and also if you want to obtain chromosome, you have to ask cells to do replication and go through cell cycle and make a butyl metaphase spread. And also during this process, cell death can prevent cells to grow. So that's the reason, that means chromosome analysis corresponds almost all these DNA metabolism and cell metabolism. So that I think this chromosome, the result of chromosome analysis is some kind of comprehensive data about the damage of cells. And I'm very, but not only I, but also many people worry about what happened 10 years after this Fukushima accident. That means around now. Yeah. So I hope nothing happened here, but concerning the biological dosimetry, we have to establish it very, very quickly. And I think if we can have a very simple high throughput analysis using chromosome, it can apply for the accident in this area, I hope. Okay, then I'm happy to talk about the chromosome aberration first, and then at present I'm very curious about the application of the chromosome analysis in the clinical. So first part is chromosome aberrations. As you know, after ionizing radiation, so you can find some strange chromosome like this and like this, like this. And normal cells carry only 1 centromere and 2 telomeres. But this chromosome carry 2 centromeres, so we named this a dicentric chromosome. And also here it's a ring-shaped chromosome. So you know this is a very characteristic feature of ionizing radiation. And among the chromosome abnormalities, as you know, translocations can be easily transferred to the next generation of cells or daughter cells. But dicentrics and rings cannot go to the next generation so easily. So people call these 2 types of chromosome aberrations unstable, and that's the reason why we can use these chromosome aberration for the estimation of the radiation exposure just before. And for the analysis of radiation effect on A-bomb survivors, we normally use these translocations because we could examine the chromosome from A-bomb survivors. It's 20 or 30 years after the A-bombing. So we can use only this chromosome translocation for the estimation of biological radiation dose for A-bomb survivors. Okay, that's the reason why dicentric and or ring chromosome analysis have been established as the gold standard in the field of radiation emergency medicine, as you know. Of course, there are other method to analyze chromosome aberration, like as I told you, chromosome translocation. It's some kind of the sum of the radiation effect for his lifespan, and of course PCC analysis and micronucleus assay. But at present, this dicentric ring chromosome analysis showed a very good method. But the problem is, as you know, there are not so many people who can easily detect dicentric or ring chromosome because it's very difficult to do it with a black and white color information. It can be just a crossing of 2 chromatids like this. So we did a very simple trick. Just to put color on centromere with red and telomere with green. That makes it very easy to identify dicentric chromosome. Even I can easily identify 2 centromeres here and 3 centromeres in 1 chromosome and 1 centromere in ring chromosome and 2 centromeres in 1 ring chromosome. So that makes us a very efficient chromosome analysis of dicentric and ring chromosomes. So using this method, we could identify more chromosome aberration than the Gims stained sample because this is a very high dose. Yeah? Of course, it's 10 gray or 15 gray to the human lymphocyte. So the huge amount of chromosome aberration produced by this radiation, and then it's very easy for even for the well-trained person to identify all the chromosome aberration using this black and white information. This, and then also this curve fit very well, fit much better than Gims stained staining to estimate radiation dose. And now we are now using the automatically image acquisition system. So using this system, we can acquire 1,000 metaphase within 2 hours. So we have 2 hours, and then analysis by manually 2 hours. And now we are developing a new software to automatically analyze the chromosome aberration. This helps us a lot to perform the high speed or high throughput chromosome analysis. And this gives a very good point because high throughput means many cells or 1,000 metaphases, 1,000 cells, information from 1,000 cells. That makes the resolution of the chromosome analysis much higher than before. So I think, but at present there are no accident, and we don't have to use it for the accident. So then I decided to apply this method in the patient, for the patient receiving radiological diagnosis or radiotherapy for cancer. And then I think this chromosome analysis is not only for biological dosimetry, but also for the quantitative evaluation of chromosome instability and or radiation sensitivity. So I decided to have a collaboration with a clinician to do this. Fortunately, the reason why I can do such kind of work very easily is one important point, professor of the department of radiology at Hiroshima University Hospital is my classmate in medical school. So it's very easy to ask him. You have to collaborate with me. And then one more important point is the CT scan. He is a specialist of the development of CT scan. And as you know, CT scan, you cannot say it's a low dose thing. And now the development of CT scan, very high speed CT scan, expand the application of this machine. Oh, sorry. But as you know, last year, these two important papers were published. It looks CT scan can induce at least one brain cancer or one hematological malignancy in 10,000 CT scan. I don't know what is the meaning or is it correct or not, because there is so big discussion about this effect of low dose radiation by CT scan. But this is the most, I feel this is the most reliable data at present. So I really think if I can give some kind of quantitative data for the radiation risk using our DNA FISH approach, the first step is we examine the effect of CT scan on 60 non-cancer patients. And we could show the significant effect after CT scan. But you can see here, this is the increment. But the much more important point is the wide distribution of the chromosome, number of chromosome aberration even in the non-cancer patients. This was revealed only by, this could be revealed by only by the high throughput analysis of chromosome. So each point we examined more than 1,000 cells. So it's a very big amount of analysis. Then there should be some individual difference for the increment. So this is another plot. 0 means the before CT scan. So this is the distribution of the number of abnormal chromosomes from 0 to close to 15 in 1,000 lymph sites. And the x-axis shows the radiation dose in each CT scan. And we noticed that people who carry not so many chromosome aberrations before CT scan can easily increase, can stably increase the chromosome aberration after CT scan, but patient carrying a little bit higher number of chromosome aberration, it's not so clear that we can say the number increase or not. So we decided to examine this using the sample from normal healthy volunteer, and we found a quite similar tendency that patients carrying, volunteer, healthy volunteer carrying almost no chromosome aberration showed a very clear increment after low dose irradiation up to 80 milligram. But here, the person who carries relatively higher amount of chromosome aberration shows it's not clear to show the increment after low dose irradiation. So such kind of difference was diminished when you irradiate 400 milligram irradiation. So it's very good to know for the radiation emergency medicine. So from this finding, we conclude that the number of Dachshund chromosomes was significantly increased with the individual variation after low dose irradiation. And this is not only for patients, but also in healthy volunteers. So that means, of course, CT scan can increase the number of chromosome aberration, but the important point is there are individual differences in radiation sensitivity. And we next apply this method to examine the safety of low-dose irradiation, low-dose CT scan, because low-dose CT scan is a very powerful tool in the screening of high-risk person with heavy smoker for the lung cancer. And it can reduce 20% the mortality, it can reduce the mortality 20%. But still, CT is not a low-dose imaging modality, they claim. So we decided to examine the biological effect of low-dose CT scan. So the standard of CT scan, the average effective dose is 5 millisievert, but on the other hand, low-dose CT is 1/3, 1.5 millisievert. And this is the increment of chromosome aberration after standard dose CT here. We could show the significant increment after standard dose CT scan. So in this case, this is 100 patients. This low dose CT is the same 100 patients we asked to receive this low dose CT. And then we could not detect any significant increment after low dose CT scan. So this is a very good point. And then we would like to confirm it by analyzing the gamma-H foci, because this gamma-H foci correspond to the double sum breaks. So it is a very good biomarker of double sum break. It's very sensitive. So applying this method, we could of course detect the increment of gamma-H foci after standard of CT scan, but again, we could not detect the increment after low-dose CT scan. From these data, we conclude that the standard of CT led to an increment in the number of double sum break and unstable chromosome aberration, but no significant difference were observed in these biological effects before and after low-dose CT scan. So that means the application of low-dose CT for the lung cancer screening of the high risk person is justified from the biological point of view. Okay, then we move to the effect of chemoradiotherapy on the esophageal cancer using this technique. And in this case, we examine the number of chromosome aberrations during the course of chemoradiotherapy, and we found that the significant accumulation of chromosome aberration during the course, and at the final day, about 1 chromosome aberration in 1 cell. Again, we found a very big individual difference here in the increment of chromosome aberrations here. And the good point is we notice that 6 months later, the number go down to 60% from the final day. So we think maybe we can apply this for the prediction of side effect. And then gray box show the chromosome aberration from the over-responder or with the patient with severe side effect, and open box is non-other patient. And we could find a significant difference even at 20 gray timing. It's a 10 days, 2 weeks time point. And the onset of acute toxicity happened around later. So this shows that chromosome aberration can predict the occurrence of severe side effect of radiation. And one more important finding is here. So this is the increment of gamma XS foci at 2 gray point, 20 gray point, 40 gray point, and the last day by 2 gray radiation. The same radiation dose, but the increment of gamma XS foci decrease. That means the response, DNA damage response, could be weakened during the course of chemoradiotherapy. We could confirm this finding we obtained in the esophageal cancer CRT, and we confirmed this using the lung cancer patient. We had quite similar data result from the patient receiving CRT for lung cancer. So we are now preparing a manuscript for this. So now I'm sure that we can apply our new biological dose method techniques for the estimation of radiation risk by the radiation therapy. So now we can check the balance between medical. Of course, the medical benefit is very, very big, but we can introduce this quantitative analysis of radiation risk for the better handling of the medical radiation. That's all. And then these are the contributors. We have so many contributors here in this method. And this is my classmate or professor at the Department of Radiology at Hiroshima University Hospital. One more important announcement here. I would like to introduce the 6th Asian Congress of Radiation Research, which will be held together with the 68th annual meeting of the JRRS. I would also like to express my gratitude for the tremendous support provided by the society, this society, the SSR, Society for Radiation Research, especially Dr. Mishra, Bill Maggs, Singh Pandey, and Kumar, whose effort contribute to the great success of the 5th ACRR meeting. And especially Dr. Mishra helps us a lot with his wonderful international network. Thank you very much. And once again, I sincerely thank you all, and I'm looking forward to seeing you all at the 6th ACR Hiroshima next year. Thank you very much.
Thank you so much. And this kind of information, data, and investigation has become more and more relevant because of this uncertain world and the increased use of CT scans and X-rays and the angios in medical practice. Thank you so much for an excellent talk. And any questions from the floor? Yes, please.
Very nice talk. I really enjoyed it. The incidence of cancers from the ABOM survivals that you show at the beginning, it reflects how many cases?
How many cases?
Yeah, like the total number of cases.
I see. So it is quite difficult because It's a risk you can say, but almost half of them or two-thirds of them suffers cancer because normal population also suffers 1 half.
So about
So
2,000.
2,000, yeah.
Okay. Because there is a calculation that the statisticians who are using where the total number of cases is around 600. These are cases they use.
Yeah.
And what is the thing that I'm always thinking about is that this 600 cases were sort of picked on a background of cases for cancer
it's very,
of
very
about 24,000. And so the question is, how
this is
reliable is this selection?
Yeah, this is a very important point. So that means the fear for cancer is a very, very big problem, and also the social problem. The real increment of cancer is not so high, I can say, but still, there are a possibility. If you feel some possibility, it gives a very big impact to the people. Eh? This is a very big problem. Yeah. Thank you.
Yeah.
Good morning. In your data, you showed that chromosomal aberration in healthy volunteers and patient underwent CT.
Please, I can't catch.
I think one of the slide you compared the chromosomal aberration frequency
Yeah,
in the healthy volunteers
yeah.
who underwent CT, also the patient.
I think, okay, so it's very different. In healthy volunteer, the aberration of chromosome aberration in 1,000 cells is from 0 to 15. So then the increment is 2 or 3 or something like
Okay.
in 1,000. So it's very difficult to find to identify this difference with a very small number of samples or cells. You have to analyze more than 1,000 cells. Then we could detect a very slight increment by the averaging of the many patients. That's the only way to detect the public effect of the low-dose irradiation, like CT scan. Normally, it's very difficult to identify 5 milli. So probably if you have only the one data after irradiation, you cannot, after low-dose irradiation, is it by the irradiation or it's the chromosome aberration you have before? It's very difficult to distinguish. But we know that the number of chromosome aberration increases by aging. For example, in my case, until 40, I had no chromosome aberration in 1,000 cells. But when I became 50 years old, graduate student came to me, you are old, because she found 3 dissect chromosomes in my lymph site. So this could happen. It's probably this the individual difference in the chromosome aberration reflects some aging or some other stuff. Yeah?
Okay.
This is something.
The second part, anyway, already answered partially. Did you screen the chromosomal aberration in pediatric subject followed by CT?
Yeah, this is something I'm very curious about.
And also, you mentioned dicentric and ring or unstable type of aberration.
Okay. So
And how do you expect it will get accumulated over an age?
this is something I'm
Maybe a clarification. Thank you.
I'm very, very curious, but I'm originally a pediatrician, so I'm very, very curious about the effect of CT on pediatric patients. But, ethically, it's not so easy to do it. So I'm now starting from the adult. I'm now discussing with the professor in the department of pedagogy because I can order him because I'm the elder one in the field of this pediatric side. So it's very easy for me to ask him to collaborate with me. But now I'm planning to do it. But again, we need a much many volunteers who can contribute to this project. This is the problem. Thank you very much.
Thank you so much, and it was a wonderful talk. So we move on to the next one. Thank you.
Thank you, Chairperson, and thank you, Dr. Satoshi Tashiro, for a wonderful talk. We will now move on to our next session on radiation biodosimetry and biomarkers. To chair the session, it's my pleasure to invite our Chairperson, Dr. V.K. Singh, AFRRI USA, and Dr. Rajiv Ranjan, Director, Medanta Cancer Center, Patna. Please join us in welcoming him. I now request the Chairpersons to take over the session and introduce the speakers.
Good morning. First speaker for this session is Dr. Anurag Sinha, Human Space Flight Center, ISRO, Bangalore.
A very good morning to all of you. I feel extremely privileged to be in this August gathering of eminent researchers and academicians. And since last 3 days, I have been listening to the wonderful research which is happening in the area of radiation. And some of them I could understand, but most of them were beyond my comprehension, mainly because I'm from aerospace background, and I stand at the interface of aerospace engineering and medical science, mainly because I work in human spaceflight program. So before I get into the details of my slide, I would just like to speak a couple of things about the relevance of human space flight. So many of us look at human space flight as a science and engineering endeavor. That is to some extent true, but it has relevance in the civilizational development also. If you look at the history of civilizational development, the resources which has been available were always, short of the requirements, and that's why in the ancient times we had these conquerors conquering land, and then in the medieval times there were colonies by many European countries who tried to capture colonies mainly because of the resources. And in the current world order, those things are no longer possible, and the need for energy has become almost kind of infinite. The need for dealing with the pollution, the need for dealing with industries which produce dirty effluents, these are real problems which the science and technology community is really struggling to find solutions. And one of the solution which looks very attractive is, of course, going beyond Earth. And maybe 50 years back, this was more of the scene of science fiction. But today, we are at that moment of time where in our lifetime we would be seeing the colonization of bodies which are beyond Earth. And we have been in the business of launching satellites since last 5 decades. And we have got this clarion call from our Honorable Prime Minister that we have to have a human spaceflight program. And the context was that we have already demonstrated landing on Moon, and we have also demonstrated reaching Mars. So this was kind of the next logical step. So if you break down the requirement of human space flight, you need a rocket to send humans up in space, which is what you see in the middle of this slide. And then on the right hand side you see an orbital module. So this kinds of provide the habitable function to send humans up in space and bring them back safely. Of course, the problem is not that simple. If you further break down the requirements of human space flight, in addition to the launch vehicle and the orbital module, you also must have a very comprehensive mission management program, which should basically take care that the human physiological and tolerance limits are never exceeded. However, even for us, dealing with the human-centric system is entirely new, because all along we have been launching satellites and we have never launched humans. So once humans are integrated into the human space flight, then all the issues which are related to humans, specifically in the healthcare, all of that becomes an engineering problem. So in addition to healthcare, we have other things like human factors. That also becomes kind of an engineering problem, and we have been quite successful in dealing with many of these. However, the overall crew safety, which needs to be ensured in human space flight, is of course something which has to be dealt with as an integrated effort. And if you look at our roadmap of human space flight, so we have this immediate goal of demonstrating successfully sending a human to space and bring him back safely. That's the first milestone which we will be demonstrating in next couple of years. In fact, the first unmanned flight is happening early in 2025, first quarter. And thereafter, we see a big opportunity because the International Space Station currently is getting decommissioned. So India is having plans to establish a full-fledged space station by 2030. And we also have plans to go to Moon as well as Mars. So as I mentioned earlier, that humans and space, these two are like water and oil. They don't mix together, mainly because we have evolved on Earth dealing with the 1g gravity, whereas in space, if you go, it's altered gravity environment, specifically the microgravity. The environment is always very closed and hostile. We have to deal with isolation. So there is not only engineering problem, there is a psychological and psychosocial problems also which has to be addressed. And if I just list out some of the risks of human space flight, so you can see there are many, and radiation is also one of a very important human risk in human space flight, specifically related to unsafe dose exposure. And why it is, that I will tell in my next slide. So the space radiation, you cannot do away with it. It's omnipresent in space, and there are effects of space radiation, and the synergetic effect of space radiation with other space flight stressors. Not much studies have been done in this area, but if we have to go and occupy other planets like Mars, then these kind of studies has to be initiated not only in India but across the globe, because space is something which one nation alone cannot win. It has to be a global effort, and it is a global effort. So if you look at the human challenges, all of you are aware that International Space Station is already in orbit. It's at 400 kilometer altitude above the Earth. So in that orbit, most of the medical risks are already known, because that has been occupied over the last 3 decades. So most of the risks have been characterized. Some of them have been accepted, and what is not accepted, for that there is a comprehensive monitoring and management program in place. But if you have to go to other destinations in space, for example Moon, or for a short duration or even for a long duration, because Artemis program is already on board, it's an operational program, and India is also a signatory to the Artemis program. It's a global endeavor to establish a lunar space station around Moon, and then the next step is going to be Mars. So in these environments, the risks are basically unknown. So there has to be some sort of research towards the characterization of medical risks and how to mitigate them. And this question is also there, that a lot of medical data specifically related to International Space Station are already available, but most of these studies have been done on Caucasian population, and as healthcare professionals, you know better than me that the Indian body type is slightly different than the Caucasian body type, and on Indian body types hardly any medical characterization or risks investigation has been done. So there is a very detailed process of how to safely integrate a human into a space mission. So I am not getting into the nitty-gritty of this. However, what is important to understand is that even after making a lot of adjustments in the space flight hardware, as well as making a lot of adjustments in the space mission, still a normal person cannot, just like that fly to space. That's how difficult it is. That's why we have this astronaut selection and training program, which basically prepares a supremely fit and both mentally and medically person to actually go and execute a human space flight mission. And this effort of integrating a human into a space flight mission depends on the mission duration. So if it's a short mission, the integration effort is much less, but if it's a longer mission, then the integration effort is much higher. And these are very well known, some of the risks of human space flight, and the priority of these risks changes with each mission profile. For example, if you have to go to International Space Station, then the most critical health risks are injury from dynamic loads. You could have muscle atrophy or bone atrophy. Radiation is mostly known and it's an accepted risk. But if the mission changes to a lunar mission or a Mars mission, then the criticality of these health risks will appropriately change, and it has to be addressed from that perspective. Now, as I mentioned earlier, that our next goal is to go to Moon as well as go to Mars. So if you really look at the kind of radiation environment with which these missions have to mitigate, So these radiation levels are really huge. When you talk of the galactic cosmic events, it ranges up to all the way up to 1 giga electron volt. And if you talk about even the Van Allen belt, it is 10 mega electron volt. And if you really look at the Earth limits of exposure, so you know better than me that for general public it's only 1 millisievert a year. But if you go to International Space Station, the kind of radiation exposure which an astronaut faces is of the order of 80 to 160 millisievert per year. So you are getting almost 1 millisievert in just 1 week. And if you have to go to deep space, for example, if you have to travel to Mars, so by the time you reach Mars, your exposure is already of the range of 500 millisievert. And on Martian surface, again, it's going to be 100 to 400 millisieverts. And not much protection on the engineering system right now is available. The only known material which we know as of now is high density polyethylene, because it's lightweight, can be molded into many shapes, and really heavy protection cannot be launched. So that's the challenge. And there are other aspects also. For example, some of these mitigations are being done through space weather prediction, but we know that the kind of variability which is there in the solar events as well as GCRs, so these predictions are not very accurate. Then what we have is a lot of knowledge gap. For example, I'm not sure, I haven't come across what's the impact of a GCR dose on human body. And the kind of animal analogs what we are using to study some of the effects of radiation, physiologically they may not be equivalent to a human physiology. So there are some, I won't say some, but a lot of gap areas in the knowledge of radiation research which needs to be mitigated. And next I will present some of the things what we have started doing. So we have started studying the effects of radiation on extremophile. So this tardigrade is a very well-known extremophile. Right now, tardigrade experiments are ongoing on International Space Station, and we have also done experiments on tardigrade. In fact, this experiment is flying to International Space Station in April 2025. So the ground control studies has been completed, and we have seen that if you expose an adult tardigrade to 3 kilograms of radiation, almost 80% of them die. They don't sustain beyond 3 kilograms. Some of the other medical initiatives which is not related to radiation, what we have undertaken is the development of a customized healthcare system, which is going to be AI-based system. So the key deliverables in this are basically health sensors, AI-based data analytics, integrated alert system, and predictive health monitoring. I am not a big fan of integrating AI into medical, because I always believe that sending a doctor as an astronaut still is a better approach rather than having an AI-based system. But of course, these developments are being done. Then in the development of space medicine formulary also, we have done quite some work. So some of the core categories of medications which we are developing fit for space, environment, storage, and shelf life are in these areas. And some of the specialized treatments what we are working on are radiation countermeasures. So on the radiation countermeasures, so presently we are working on the protection part and not on the pharmacological part. The vestibular suppressants also is something what we are working on, and immune boosters. So the main effort of R&D is of course packaging and dosage considerations for space usage of these commonly available medicines. Then studying the effect of microgravity on the musculoskeletal system is also a big endeavor which is happening. So here a very well known microgravity analog, which is a 6-degree health tilt study, is being done, and a lot of science is being done in this area. So those were some of the initiatives what we have started, but we have huge opportunity of research, of supporting research in healthcare domain in the area of human factors. Some of you may be interested in taking up collaborative research opportunity with our organization, specifically in the area of space radiation. So we are looking at the environmental monitoring prediction, as well as the medical side, which is the effect on immune system, and the countermeasure development, both on the engineering side as well as on the pharmacological side. These are some of the other areas in which we are ready to do collaborative research. Then habitability and environment factors are also the areas which are very relevant for human space flight, and human adaptation and countermeasure development. These are also again very, very pertinent areas. I'm sure some of you may be interested in doing some of this research, and we'll be happy to collaborate. Again, in the area of space medicine, medical informatics-based healthcare system, the monitoring part, the operations, and the rehab part are some of the areas in which we are very much interested. So that's all from my side. Thank you all for patient hearing.
Now this talk is open for questions or queries from the audience. Yes, Dr. Pandey.
Yeah. So Dr. Sinha, it is very nice talk, especially from ISRO angle. I got one question that you have mentioned that criticality factor, radiation carcinogenesis as factor 4 in one of the slide. But however, if we see this literature from the NASA or other space radiation biology programs, not very well concrete radiation carcinogenesis reported in this space mission programs, astronauts and other places. So what is criteria of putting this carcinogenesis as a criticality factor 4 when there is not much details are known, or and dose also is only 0.5 gray, 500 millisievert over the year. So this is one question. The second question is that if you look for the microgravity and the highlight radiation, especially for alpha or maybe proton is one of the neutron. So is something known that in microgravity condition, whether the biological response is different, especially for generation of harvest or DNA damage, whether something is known. That is something very interesting area to be investigated.
So let me first answer the risk matrix. So NASA's risk matrix is entirely medical evidence based. These medical evidences they have collected over last 30 years. We are new entrants to human space flight. We do not have medical evidences to that level. So many of these risks have been characterized based on engineering knowledge and published literature. And specifically, if you really look at the effect of radiation on space flight, and what is known till now is the studies which has been done on astronauts who have visited International Space Station and have returned back safely. So till date, no known cases of cancer due to space flight has been reported in astronauts. There was one study done recently where they have observed that there are some genes whose expression increases in space environment. Around 311 genes were identified whose expression increases in space environment, and those genes were mostly responsible for skin barrier damage and inflammation response. So there hasn't been that kind of correlation between human space flight travel, direct evidence of cancer and human space flight travel. And the reason could be because the astronaut population till even now, after 5 decades of human space flight, is very small. Hardly 50 or 60 astronauts have actually flown to space. And once these numbers increase, maybe we will have better data on the correlation of space radiation and maybe cancer. And your second question was on the microgravity. So I think so I answered that also. The synergetic effect of radiation with other stressors of microgravity has not been investigated in a synergetic manner. Most of these effects have been studied in isolation, and there also the participants or volunteer numbers have been very, very small. So if you look at the kind of volunteers which are needed, for example, drug trial, those kind of numbers have never been studied in any human spaceflight program. So that's something which we have to, consider.
Any other? Yes, Dr. Mitra.
Yeah, I'm Dr. Mishra from Bahaba Atomic Research Center. I would like to appreciate your participation in this gathering because we have been looking forward to collaborating with a space organization for space radiobiology research program. My colleagues are very excited over collaboration. It's all open to talk to us, and we would like to participate in it. So that's one part. The second part is you mentioned that there is no observed cases of cancer induction in astronauts, also particularly because of the limited study and also limited number, both. I would like to imagine that at your center, do you have a model laboratory where the microgravity and the mixed radiation effects can be studied? Because in space, you will have mixed radiation, not just alpha, or not just neutron, not just gamma. So that's the issue which is central to radiobiology research. I would like to hear from you.
So we have a radiation facility. That radiation facility is basically for testing of electronics. It's not human rated. So that facility is primarily testing because our satellites also has to operate in radiation environment, and our general electronics have this tendency of getting damaged because of the energy deposition which happens because of radiation. So we have a facility where we screen electronics for space application, and we have a separate facility which is a 6-degree bed tilt facility, but we haven't integrated, we haven't yet developed that courage to, integrate both of them.
Okay.
There are ethical issues involved, I'm sure there would be, of testing humans in a radiation environment, and we are not expert in that area, and we are open to collaboration and address all those issues. And of course, the research part has to be conducted by people who are experts in this area. Our role is going to be kind of a facilitator.
Sure. The last question I have is that, is there concern in a space research program of the diseases or physiological effects on human body other than cancer?
Of course, the biggest challenge of going to space, and if you would have observed the recent picture of Sunita Williams,
Yes.
she looks, almost shrunk in size. The main reason is the moment you go to space, this muscle and bone atrophy is something which happens. And the second part is the nutritional requirement of working in space is like consuming almost 4,500 kilocalories of food in a day. Not everybody can really eat that much. That's also one of the challenge. So you
Sure.
have this problem of muscle and bone atrophy, and then this requirement of having this much of nutritional intake, which everybody is unable to cope up with. So that is why we have these issues.
Yeah, very good. Sure. Have we learned any lesson from Sunita Williams staying for a long time in
Yeah,
international?
it's there for all of us to see. You know, she has really become very, very. She looks very undernourished if you really look at, and I'm sure her immune functions and all would be compromised, and she will have to go a very long rehab cycle once she lands back on Earth.
Thank you.
It could be,
Thank you.
more than a year kind of rehabilitation we are looking at.
Thank you, Dr. Anurag Sinha, for your wonderful talk. And I'm going to hijack this session for a few minutes for something else. Thank you, Dr. Sinha. We came from US to attend this meeting, and we are very much impressed for whatever is going on here and how Dr. J.K. Singh has arranged this meeting. So we are going to give some from our side. There is some appreciation for that, specifically for Dr. J.K. Singh, but I'm holding him for a minute because Dr. Hugoel had to leave and his car is waiting. So first, I would like to request our director to come to the dais to thank few of people here who have really contributed for that meeting.
We request Dr. J.K. Singh, Director Organizing Chairperson, to felicitate Dr. Anurag Sinha, Deputy Director, ISRO.
Okay, 1 minute, Captain. First, Dr. J.K. Singh will first felicitate. Oh, okay. This is AfriCoin, and it is for appreciation for Dr. J.K. Singh's efforts and wonderful arrangement or excellent hospitality. And beauty behind this coin is this coin can be given only by head of the institution, that is only AFRI director can use, and AFRI director is here, so he appreciated Dr. J.K. Singh. Thank you, Dr. J.K. Singh, for your all wonderful arrangement and whatever hospitality you extended to all of us. So thank you very much. Thank you. You were called for felicitating last speaker, so please finish that also, then I will call Dr. Hugoel.
I request Dr. J.K. Singh, sir, to felicitate Dr. Anurag Sinha.
Before coming here, we had gone to Mumbai, and we came across Dr. Misra and Dr. Hugoel there, and they extended us wonderful hospitality there also. So I request Dr. Hugoel to come to the dais to accept the coin from AFRI director. Professor K.P. Misra. Sure, sure, Doctor.
My appreciation to Dr. Singh and Dr. Burke, Captain Burke of AFRI, to leave behind a memory in terms of this medal that you have given to me and to colleagues. But I tell you, this is more than a medal. We value it from our heart of our close relation later in future in science as well as in interactive program.
Sure,
Thank you very much again.
Sure, thank you very much from our side.
Yeah, okay.
Brain behind this society and meeting is Dr. B.N. Pandey.
Yeah.
He worked tirelessly for very long time to arrange it and make it successful. So I would like to request Dr. Pandey to come to the dais and accept coin from Captain Bark. Few more minutes. Give me 2 more minutes. 2 more minutes. You have one young blood who worked for very long hours and extended extreme sincerity, and everything was on the time, immediately responding any mail, and to what extent he supported us here during this visit, I don't have words and I won't tell everything here, but he has done something extraordinary. So I would like Dr. Sachidanand Behra to come to the dais to accept the coin. I know Dr. Pritanjali Singh is not in the audience. But yeah, beautiful. So we will give it, Captain Burke will give that coin to Dr. J.K. Singh for Dr. Pritanjali Singh so that it can go to her. We are very much thankful to her for arranging this conference here and serving as organizing secretary. So thank you very much for everybody. I'm coming. Next talk during this session is by Dr. Prabodh Kumar Meher. And title of his talk is Degree of Intra and Inter-Individual Variability in Radiotherapy Induced Translocation Frequency as Biomarkers of Risk for Second Malignant Neoplasms. Dr. Meher.
Yeah, good morning everyone. My name is Prabodh and I am working in Stockholm University. I thank the chairman for the kind introduction and the organizing committee for giving me this opportunity to show some of our result what we are working in Stockholm University. And yes, today I am talking about degree of intra and inter-individual variability in radiotherapy-induced translocation frequency as a biomarker for risk of second malignant neoplasm. This is a part of a bigger project called Symphonia here, and we are working in collaborations with several partners. And all of persons are names are here. And to begin with this talk, let's first understand the individual response to ionizing radiation exposure. Day before yesterday, Andre Wasik gave a very explanatory detailed talk about how if there is a genetic component on the individual response to the radiation. So we all know that every person's, each body reacts differently to the radiation exposure. And this results in varying individual susceptibility. But then the questions comes in this bigger project where I am working is, does having had cancer before affects the individual susceptibility for second cancer, that is second malignant neoplasm? That is what on this project we are trying to understand. And to get into it, we need to understand the individual sensitivity to ionizing radiation. And to understand the individual sensitivity, we know that chromosomal aberrations in peripheral blood mononuclear cells are often analyzed as a biomarker to exposure, and also we can use it to understand the individual sensitivity to ionizing radiation. Whether we can use it or not, that is a big question among the scientific community, and we are trying to understand this from the patient's perspective. And however, if we took chromosomal aberrations to understand the individual sensitivity, then there are two major types of uncertainty while we analyze these results gathered from the whole patient. And these uncertainties we can define broadly in two categories. One is random and the other one is systematic. And if we look into the random, it is the environmental factors that influence the response of the lymphocytes of the human blood when it gets exposed to the radiation. And the systematic one is when we quantify the chromosomal aberrations, the distribution pattern of the chromosomal aberration in a large cohort of the patient, like Poisson distributions. It's a systematic uncertainty. And all these uncertainties has certain pros and cons. And the cons of the random uncertainty is that we need very repeated blood sampling from a donor, which is quite a difficult task to ask a donor to give blood several times to study this. And for the systematic uncertainty, we need to score many more cells, like many more patient samples. The more we include, the better we will have better will resolve this uncertainty. And if for this purpose, if we are considering chromosomal aberration as an individual radiosensitivity, for a proper interpretations from the cytogenetic results, a test to measure radiosensitivity, it is really important to access the difference between intra-individual and inter-individual variability in response to the ionizing radiation. That is what we wanted to understand. So if we look what is inter-individual variability, it is the response of different persons to ionizing radiation, like how different persons respond to ionizing radiation. Here we are talking about chromosomal aberrations, but it can be any other thing. And on the other aspect, an individual person can respond to the radiation differently in different time or different situation. If you remember the talk of Andre Wasik, how a person responds in different season and different time. So this is what we call intra-individual variability. So this we need to understand a little bit of it, and to understand all these things in this project, our experimental approach was to collect the patient samples who were going for the radiotherapy treatment. And for this purpose, we have included 300 patients in the study, and these patients are coming from Sweden, from Poland, from Belgium, and out of these 300 patients, 200 patients are primary cancer patients and 100 are secondary cancer patients. And out of these patient samples that we have collected, we are studying the individual mutations level and the radiation sensitivity biomarker and also genetic biomarker. To give you an idea how it is being done is for individual mutation level induced by radiotherapy, we are collecting the blood samples from the patient 3 times. The first one is before radiotherapy, and then the patient completes the radiotherapy, and once the radiotherapy is done, then we collect another blood samples after 1 week, and then we get another blood samples after 4 weeks. And in these blood samples, we look for the individual mutations level using fluorescence in situ hybridization assay, that is FISH, to look for the chromosomal aberration. And for the other study, that is for genetic biomarker for second malignant neoplasm among these patients, and we get the blood samples from these patients. Those are brain cancer, lymphoma, and breast cancer. We also include this 100 secondary cancer patient here for the SNP array study. So we want to look to the whole SNP to find if we can find some genetic biomarker for that. And the third one is the radiation sensitivity biomarker assay. And for this, we are collecting the blood samples 3 times again. That is before radiotherapy, 1 week after radiotherapy, and 4 weeks after radiotherapy. And then we are looking for the DNA damage in them using gamma H2 exposi, and also we are looking for the micronuclei in those. And in addition to the basal level of this, we are also irradiating those samples with 2 gray of ionizing radiation, in vitro irradiation, to check their sensitivity. But in this talk, I will be majorly discussing with you with the initial results from the individual mutations level induced by radiotherapy. Yeah, to study the individual mutations level, we are using FISH assay, and in this FISH assay, we are using the whole chromosome paint for chromosome number 1, 2, 3, and 4. And in our setup experiment, we have whole chromosome painted in red for chromosome 1 and 3, and chromosome 2 and 4 are stained with green, and the other are counterstained with DAPI, that is blue. And if we consider why we consider these 4 chromosomes, yes, these are the largest chromosome in the human genome, and we cover about 15.37% of the total genome if we look into the percentage of DNA content from this chromosome. And what we are looking at in the FISH, if you look into the this image in the A, this is a control cells like the without irradiated cells, and here we see the red and green chromosomes all are quite okay, nothing happened. And here this is a cell showing translocations here in the chromosome number either 1 in red or 3 in also in red. So either this translocation involves chromosome number 1 or 3. So this kind of translocations we are quantifying in this assay. And we also had a dose response curve with this including chromosome 1, 2, 3, and 4, and we found a very nice dose response for this. But coming to our first set of data, like how these chromosomal aberrations are showing in the patient samples. This is, as I said, this is a preliminary data. We are still collecting the data and gathering everything together. But to get a first glimpse how it is coming out, if you look, these are the different cohort of patients. These are the brain cancer patient, and this is the breast cancer patient, and this is the lymphoma patient. And this N is the number of patients that are included in the study. So if you look into this breast cancer patient has a quite large number, that is more than 100 patients. So we are more focused on the breast cancer as of now, but in the end when we accumulate all the results, then we can say very concrete output what we get. So if we look into here, then what we found is radiation has a clear impact on the frequency of aberration that you can see in specifically in the breast cancer patient. This 0W is before radiotherapy, and after radiotherapy we see an increasing pattern of chromosomal aberrations and in breast cancer and in lymphoma cancer patient. But we have a very contrasting or opposite result in case of brain, but the number of patients included here is 7, and it is mostly because there are 2 patients which were shown some outliers, and that is what it is contributing here. So anyway, we found that there is a clear impact of radiotherapy among these patients, and that is what this pattern we see. So then we wanted to see if there is any correlation between these aberrations that we are getting in these cancer patients. So we did a correlation study of these cancer patients in 0 week before radiotherapy and the average value of the 1 to 4 week of radiotherapy. And we found a very weak correlation here, but it is a very quite significant, and here the number of sample of the patient is 84. So this aberration frequency is somehow correlated as well. So then we wanted to check if there is a correlation between the aberration frequency and the tumor dose. And if we look at here, we have the tumor dose here in the x-axis and the aberrations per 100 cells. And we couldn't find any correlation here. And this was a quite bit surprise to us. Like we see a correlation of the radiation effect of the radiotherapy, but if we look into the tumor dose, there is no correlations. Then we went to the clinicians to ask what is happening here, and they clarified us because we have received samples from 2 different collaborators, one from Ghent and another from the Belgium. And we found and they informed that the patients were treated in Ghent and Kiels with IMRT with 6 megaelectron volt photon, but using different technique, and it is the clinicians who decide how to treat with the patients. So I have no much knowledge how the clinicians play in the hospital, but that is what it is affecting. So then we recalculated these things using the tissue volume which is receiving more than 2 gray of radiation dose, and here when we correlate this chromosomal aberration, then we found, although it is a weak, the R value is 0.42, but it is still a significant correlation when we looked into the raw aberration data. And this significant correlation demonstrates that the aberrations in what we are seeing are meaningful in the, although there is a high level of variability. And this high level of variability, what we have seen here is already earlier reported in the literature. So we know that this variability is coming, but it's very interesting to see that it is correlating as well. Yeah, then our goal was to understand the inter-individual and intra-individual variability, and it was a bit difficult to get a concept how to interpret it. So what we do is we express this inter and intra-individual variability in terms of coefficient of variation. And how we do it is we took, this is just an example, don't go by the number hardly, but yeah, if these are the 3 random patients, and this is for the patient number 1, this is week 0, that is before radiotherapy, week 1 after radiotherapy, and week 4 after radiotherapy. And if we are looking into the aberrations in 100 cells, then if we are saying the intra-individual variability within this patient number 1, then we take these 3 value and we found the coefficient of variation. And likewise, the intra-individual variability for the patient number 2 will be like this, and patient number 3 will be like this, 0 week, 1 week, and 4 week. And then the inter-individual variability, if we want to count, then of course it is very straightforward. Someone will say, okay, take the value of the patient number 1, 0 week, and patient number 2, 0 week, and patient number 3, 0 week. This should be the inter-individual variability. But now we want to compare. So then the inter-individual variability will be lower than the intra-individual variability. That's why we choose to take the 3 random patients, the 0 week from the patient number 1, and the 1 week from the patient number 2, and the 4th week from the patient number 3. That is how we count the individual variability or the coefficient of variation among these random patients. And when we looked into it, then you can see here the red bar is the intra-individual variability and the green is the inter-individual variability. And there is, both the values are almost at the same level. And what we could say here is, if there is any intrinsic radiosensitivity, if at all it is present there, it is masked by the measurement of error. That is what we discussed in the beginning, how uncertainty these are. So we need to include more data to get more concrete result. That is what we are thinking as of now. Yeah, coming to the summary, we can say with this preliminary data that radiotherapy showed a clear impact on the frequency of aberrations in the lymphocytes of Hodgkin lymphoma and breast cancer. We couldn't say many more things from the brain cancer because the patient numbers were low. And the second one is the breast cancer patient showed a weak but significant correlation between spontaneous frequency of the aberrations before and after radiotherapy. And then the third one is the significant correlation between raw aberrations and the tissue volume receiving more than 2 gray of radiation dose demonstrates that the aberration yield what we are seeing are meaningful despite the high level of variability. And similarly, although we found a similar coefficient of variation value for the intra and inter-individual patient, it suggests that if there is any difference in the intrinsic radiosensitivity are hidden by the measurement of error. And although this is an ongoing analysis, I presented a preliminary data to all of you. But in addition to this, we are in this bigger project, we are also looking into the micronuclei data and also to the kinetics of DNA repair and also the genetic biomarker for second cancer using SNP array. So when we have all this data, we will have more conclusive result on it. And also we are in vitroly irradiating the patient samples with the primary cancer for gamma H2X and micronuclei. That will also give whether this assay can be used as a biomarker for second cancer. But we are not conclusive here yet. So this combined result will yield more complete picture of the potential use of lymphocyte of patient sample as a material to access individual radiosensitivity, or any of these assays that we are trying, like the chromosomal aberrations or micronuclei or gamma H2X as a biomarker for second cancer risk. Okay, with this I wish to acknowledge my very cheerful group at Stockholm University. This is my group leader Andre and other colleague here. And most importantly, I wish to thank the work package 4 members from this bigger project Symphonia and all these members from the Poland and GAN. And I also wish to thank the Symphonia which was sponsoring or funding this research work, and also to our generous supporter of funding of Swedish Radiation Protection Agency, and not but the least the Stockholm University and Department of Molecular Bioscience where I am working. And I wish to thank you as well for your kind attention. And if you have some comment or questions, I will be happy to take it. Thank you very much.
One brief question, Dr. Venkatachalam. We will take only one question, please. We are running out of time.
Is there any specific reason why you have selected chromosome number 1, 2, 3, and 4?
Yeah, thank you
Because
so much.
it covers only 15% of the genome. Also, there are literature that translocation frequency is not directly proportional to the DNA content. If at all there is any hotspot of the chromosome which you have selected, I don't think it will represent the individual radiation sensitivity. Can you comment on this?
Yeah, thank you so much. The first part of questions that you ask, why we choose chromosome number 1, 2, 3, and 4 is because see, when all these treatments are being done with the photon, the low LET radiation, so the chances of getting the chromosomal aberrations, these are the largest chromosome in the all the 23 pair chromosome. So that's why we chose. And And if you are asking why we have not chosen all chromosome or 50 chromosome or 50% of total genome, I think it will be more costly to get all the whole chromosome paired, so we need to also be little bit economical in that perspective. And we know that from even if we get the total genome coverage of 15%, and because the low LET exposure is normally a homogeneous exposure, so we can always calculate how much more chromosomal aberrations we can get if we are getting specific amount of chromosomal aberrations from 15% of chromosome. I hope I answered to your question.
Okay.
Thank
Okay,
you.
Dr. Meher, you take the question, but I will request you to just interact with him at personal level because some speakers have flight they are going to meet. So please ask the question and I will request him to interact with you.
Okay, so one brief question. So could you examine the effect or side effect, the relationship between side effect and of the radiotherapy with this translocation? Because I'm very curious about it.
I couldn't hear you, maybe I will interact with you there.
So translocation, are there any relationship between the translocation and the side effect of therapy?
Sorry, difference between?
Translocation and side effect of
Transportation and site of testing.
Side effect of chemotherapy or radiotherapy.
Aha, okay, side effect
Because
of
we
chemotherapy or
examine the
radiotherapy.
dysentery, but you examine the translocation, so I'm very curious about it. How about it?
Yeah, we have the patient data, whether these patients have received chemotherapy or other type of therapy like hormone therapy or something before they were given the radiotherapy. And once we have all this data all together, then we'll interpret in specific to the radiotherapy, then we'll look back whether it is related to those things as well.
Okay, thank you.
And that's a crucial thing. Thank you so much.
Thank you, Dr. Meher.
Thank you so much.
Very good morning to all of you. In this session of radiation biodosimetry and biomarker, the next lecture is by Sophie Dobiach from Technical University of Munich, Germany. Floor is yours.
Thank you very much for the kind introduction. So good morning, everyone. So as I already mentioned, my name is Sophie Dobiach and I'm a clinician scientist and radiation oncologist at the Department of Radiation Oncology at the Technical University in Munich, and I'm really happy that I get the opportunity to give a talk about some research that is ongoing in our department. So the title is Targeting Radioresistance by Novel Treatment Strategies in Different Advanced Pancreatic Tumor Models. So first of all, I would like to give you a short introduction about pancreatic cancer. So the most common type is the pancreatic ductal adenocarcinoma, so short PDAC. And pancreatic cancer is one of the most lethal human cancer entities. Although there is a lot of research ongoing, the prognosis for these patients didn't improve over the last years. So the mean survival is still very poor with 6 to 8 months, and the 5-year survival rate is less than 10%. So one of the reasons for this really poor diagnosis and prognosis is the high heterogeneity, leading to a resistance to standard therapies, including radiation and chemotherapy. So it's still an unsolved health problem, and it is noticed that the incidence is still increasing, and therefore it is expected to be the second leading cause of cancer-related death in 2030. So coming now to the clinical treatment of these patients. So the only curative treatment option for patients with pancreatic cancer is the surgical resection, but only the minority of 20% of the patients are initially at a primary tumor stage that is resectable, and the majority is in a locally advanced tumor stage. So I really would like to focus and to mention that the survival depends on the resectability. So as you can see here, for patients with a resectable tumor disease, the median survival is 20 till 23 months. And for patients with a locally advanced tumor, if we apply a neoadjuvant therapy, so chemotherapy or radiation, and if the patients get the chance to undergo a secondary resection, then the median survival is similar to the survival of the patients which are in an initially resectable tumor stage. And so therefore the goal of our research is that we better understand the radioresistance and to develop strategies to really undergo the high therapeutic resistance to improve the outcome of these patients. So today I would like to present you some in vitro data that we use different PDX cell models, and we also established a workflow for the in vivo model and developed some novel combined treatment options and leading to a radiosensitization, and the overall aim would be to realize personalized radiation oncology in pancreatic cancer patients, to select the patients which benefit from the radiotherapy and to further improve the efficacy of radiation. So we use different human and murine PDX cell lines. So the murine PDX cell lines are generated from genetically engineered mouse models, and one of the advantages of the use of murine PDX cell lines is that they represent the PDX subtypes that are already known in humans, and therefore they reflect the genetic, morphologic, and clinical heterogeneity. As well, to going a little bit more to the clinical side, we also use human established cell lines, so they are either from primary tumors or from metastasis sites. And to really realize a translational research, we also use patient-derived organoids. So these are generated from pancreatic cancer tissue from the patients, either by surgery, fine needle aspiration, or biopsy. And they are grown in matrigel with different growth modulators, and therefore they maintain the similarity of tumor morphological and dynamic characteristics. So as you already know, so we have different assays to determine the radiosensitivity. So as a broad screening method, we use the Alamar Blue proliferation assay, and we validated the data with the gold standard, the colony forming assay, and for the 3D models, we use a cell viability assay. So now coming to the results. So we could show the high heterogeneous radio response in our different PDX cell models. So we screened in total over 70 murine PDX cell lines by the proliferation assay. And as you can see here, we have a radioresistant cohort and an intermediate cohort and a radiosensitive cohort, and we validated the data in our CFA. So now we also used more advanced tumor models, so the 3D models, as already introduced yesterday by Professor Niels Cordes. We got the chance to learn this technique in his lab, so we established in our department for the murine PDX cell lines the 3D extracellular matrix model, and again here we have a broad heterogeneity in the radiation sensitivity. And to enable the translational research, we also observed these findings in our data with the patient-derived organoids. So here again in red shown the radioresistant cell lines or PDO lines, and the intermediate and the sensitive. And we also correlated the morphological with the microscopic response. So here you can see the untreated, unirradiated PDOs, and here with increasing irradiation dose. And you can see that the size and the number of PDOs decrease by increased dose. So the next step was to have a deeper look in the mechanisms behind the radioresistance, and therefore we used proteomic and phosphoproteomic analysis, where we included radioresistant and radiosensitive murine PDX cell lines, and we found that phosphorylated levels of proteins involved in FAC activity were elevated in the radioresistant cell lines. And furthermore, we identified a molecular network involved in DNA damage response, so for example ATM and CHEK1. And I would like to go a little bit more detail in our results targeting CHEK1. So we used a combination treatment with a direct FAK inhibitor rabucertib, and we could show that there is a radiosensitizing effect by this combination treatment, and have a look on the mechanisms behind. So one potential mechanism would be an increased T2 MRS at the time point of irradiation due to the combination of rabucertib. Another approach was to perform a gene set enrichment analysis. There we include in total 20 murine-PDAC cell lines, so the 10 most radioresistant and the 10 most radiosensitive cell lines. And we observed a strong expression of the unfolded protein response pathway in the radioresistant murine-PDAC cell lines. And as you can see here, there are in total 3 different arms or targets of the unfolded protein response, so IRA1 alpha, then AT6 and PERK, and today I would like to focus on the IRA1 alpha pathway. So again here we performed a combination treatment where we use the direct inhibitor KIRA8, and again we could show a radiosensitizing effect by this combination treatment, and the potential mechanism behind this radiosensitization might be the increased radiation-induced apoptosis by KIRA8 48 hours after irradiation. Now moving on, and I would like to present our experimental in vivo workflow. So of course starting with the tumor cell models, and then on a weekly basis we monitor the body weight, the tumor volume and the behavior of mice, and after tumor growth we start with the imaging, treatment planning and high precision irradiation, and then followed by imaging on a weekly basis, and the endpoints might be evaluation of tumor response, toxicity and survival. So I would like to introduce our autotopic tumor models. So we established both a xenograft model while we use established human pancreatic cancer cell lines and the patient-derived organoids. So we implant the cells directly into immune-suppressed nude mice via a small laparotomy, and it depends on the tumor cell line. After tumor growth of 3 to 8 weeks, we can observe and detect a solid tumor. And so to have the advantage of our immune system, we also established a syngeneic tumor model where we use the murine-PDAC cell lines in immunocompetent black 6 mice, and there the tumor growth is very fast, so 1.5 weeks. So we are really lucky that at our department we do have the SARP system, the Small Animal Radiation Research Platform from the company Icrr. There a cone beam CT is integrated in the irradiation device, and therefore we can realize an image-guided radiotherapy, so like it's common in the clinical setting. And for this purpose, we first optimized our imaging. So here in reddish, so the hypodense structure is the autotopic tumor, and then you can see here the organs at risk, so the kidneys, the bowel, and the spinal cord. And for the autotopic tumor model, I usually perform a single arc technique where the gantry rotates from 178 to minus 178, resulting in a quite impressive dose volume histogram where we have a maximum dose in our target volume while sparing the normal tissue. So for the subcutaneous model, the workflow is a little bit more easy. So as well, we use the image-guided radiotherapy, but we don't need a contrast agent. So we use just the native CT imaging, and in this case, we arrange 2 different beams in an anterior-posterior, posterior-anterior technique. And as we don't have any organs at risk, but we do have an optimal dose in our target volume. So now coming back to the in vitro data, so just to once again remember, the rabucertib was the CHEK1 inhibitor. We validated the in vitro data in vivo in a syngeneic subcutaneous tumor model. And first of all, the good news, we couldn't detect any toxicity. So we inject the rabucetib intraperitoneal in total 14 times, and we performed a 10-gray irradiation of the subcutaneous tumor, and that was followed, of course, by tumor volume and survival and histological approaches. And as you can see here in the Kaplan-Meier curves, we didn't see any influence of rabucetib compared to the control. So we had here similar median survival data, but we could see an improvement of the median survival after irradiation, and especially we could also observe the increase of the survival by the combination treatment, so the median survival was not reached in this case. So similar results by the Kira-8 and irradiation. So it was also applied intraperitoneal, and so I don't want to confuse you because the median survival dates are different for the control and the irradiation in comparison to the data with the rabucetib. That's why, because we use different cell lines in these different models. And here again, we could not see any influence on the survival by the Kira-8 compared to the control, but also again an improvement of the survival by the single irradiation and a significant increase of the median survival by the combination treatment of Kira-8, so the UPR inhibitor and irradiation. So now coming to the summary. So I presented you today our platform of different in vitro models using 2D, 3D, murine and human pancreatic cancer cell lines. So as we observed a heterogeneity in the radiation response, we can reflect the clinical situation with our models. And I introduced you our workflow in vivo. So we established an image-guided radiotherapy for the orthotopic models as well as for the subcutaneous models, and we were able to validate our in vitro data in vivo. And I introduced you two maybe innovative targets, so the CHEK1 and the UPR, that might be one time a potential novel treatment approach for our patients. So I would like now to end with my acknowledgement. My special thank goes to my head and supervisor of our department, Professor Stephanie Koms, and to our physicist, Professor Jan Wilkens, and of course to all of my collaboration partners in Munich. And last but not least, I would really like to thank Professor Niels Cordes for sharing his technique with us and really great inspiration. And now I'm really happy to take some questions.
Sophie, thank you very much for this very good talk. And I think this is a very nice example for translational medicine, because you used relevant models and really mimicked, not only with the models, but also with your treatment planning and your irradiation approach, the clinic. So this is really of utmost importance. I think this is to highlight here. My question is, you have the three approaches. What is your top candidate which you would like to proceed?
Into the clinic?
Into the clinic, or yeah, that
So-
would be the best.
So for the combination treatment?
Yes.
So I think not the Cura-8, because there are not many clinical data available right now, so therefore it's always important to go with a FDA-approved drug. So I think rabucetib really showed impressive data so far, so I think that might be a good idea. And also I didn't show this data to you today, but we also observed already sensitization by defactinib, so there are already clinical data running, so therefore that might be an easy next step.
Yeah, so
Excuse me,
Doctor,
we
may
cannot
I ask
take
just
one
half
more.
question. Half question
Okay,
is
please,
allowed. Yes.
question, and
So
she can
I
answer
just,
you afterwards.
So I could just follow your summary slides. So it's my congratulations for all the work. So you suggested to target FAK, focal adhesion kinase, and UPR, and in pancreatic cancer. And we know that the PDAC, pancreatic, is highly metastatic, right? So as we know that there is a crosstalk between the receptor tyrosine kinases and some of these metastatic mediators, as you have showed, like FAK and UPR. So what do you think of combining a RTK, which is supporting the survival and proliferation of PDAC cells or PDAC cancer cells, in combination with some of your rational targets like FAK and UPR? That way, I think we can better control the tumor and also its metastatic propensity. I would like to have your thoughts in this regard. Thank you.
Is there time to answer, or should we transfer to the tea break?
You can personally interact with.
Okay. So
Thank you,
again.
Sophie. The next
Thank
lecture.
you to allow.
The next lecture is by Dr. Damodar Gupta. He's from Aiims, Delhi, and the topic of presentation is mitochondrial integrity and dynamics in radiation responses. Dr. Gupta.
Namaskar. Thank you so much for a kind introduction, sir. Basically, we belongs to Defense Research and Development Organization, where we work for armed forces, and our aim is not only to develop strategies to assess the effect of radiation on cells. Along with that, our job is to look for the protection modalities also. So how to protect an organism or cell or human being from deleterious effect of ionizing radiation. So today I'm going to share a part of our research that is related to the mitochondrial dynamics and how this dynamics is changed because of radiation exposure, along with the few work that we have done with the changes in mitochondrial dynamics and how we can use this particular dynamics for achieving radiation protection within the organism. So before I go to the next level, we knows about all our previous speakers. They have shared about their experience related to the high rate radiation and low linear energy transfer radiation. So aim is to understand how biologically or on molecule from chemical or from atomic level, how the damage moves from one atom to the molecule, from molecule to the cell, or biomolecule, from biomolecule to the soil and from the tissue. So all depends on the amount of energy that is absorbed by the atom. So the chemical or physico-chemical reaction and thereafter the biological consequences, it depends on the type of radiation. Along with that, the amount of energy or heat or shock or mixed type of radiation, that also plays major role in case of moving the radiation or effect of radiation from one cell or molecule to the organism level. And one part that I'm going to share about the mitochondrial dynamics. Even though we worked on the DNA damage as well as the effect of radiation from cellular level to the organism level, I'm going to share about the mitochondrial part only today. So how mitochondria, from beginning of our school, we know that mitochondria is powerhouse of the cell. So from this particular part, if we understand that how mitochondria is important, it is not only a powerhouse of the cell. It plays major role in cell death, along with the generation of heat, and the availability of calcium ion plays with a major role in relation to the changes in the mitochondrial dynamics and cell death. So energy is equally important for radiation-induced damage, for repair and recovery of radiation-induced damage. So we have two different kind of mitochondria as soon as we are exposed to the cell. One is the diseased or the ill mitochondria. So mitochondrial dynamics, that is related to not only the availability of mitochondria within the cell, like cellular vicinity around the various cell organelles, it plays major role in relation to the fusion and fission dynamics, along with the providing energy to the cell. So the mitochondrial inheritance, why mitochondria fuses? just to overcome from the stress if there is ill mitochondria or diseased mitochondria. And why fission is there? It could be because of stress. And all this dynamine related protein or fusion and fission dynamics, it plays major role for moving the cell either towards the cell death or towards the survival. So we have used two different type of radiation, either it is gamma radiation or high linear energy transfer radiation that is available in IUAC, Inter-University Accelerator Center, that is available in Delhi, where we use carbon ion beam. And we expose normal cells or transformed cells and then try to understand that how mitochondrial integrity or dynamics changes with the different type of radiation exposure to the different type of cell. So we have used almost 20 or 25 type of cells along as per their resistance, and then we did survival study, and as per the survival studies we chose the dose LD90 or inhibitory concentration, inhibitory radiation dose that can inhibit or kill the cell by 90% or 80% for radiation protection study. So this study was very much required to do. So how high linear energy transfer or carbon ion affects, all of us knows as a radiation biologist that there is linearity, while in case of low linear energy transfer radiation, shoulder is there. So you can see the changes in survival of cell following different doses of gamma radiation from 1 ray to 6 ray. And then we tried to use a molecule after performing high throughput screening, that is menon. It is available in our food sources. Even it is being taken as a nutraceutical across all over the globe. In Japan, people use it as in the soup and other. Even for gut microbiome or health, improving the health of our gut, it is being taken as a nutraceutical. So we have used menon oligosaccharide, even though it is very specific molecule, that is mannose sugar, 4 mannose sugar which are linked with the beta 1,4 linkages. So it is linear molecule, not very high molecule. It has 668 kilograms per or atomic mass unit as a molecular weight, and we use this particular molecule for radiation protection study. So it is generally considered as a safe biomolecule or molecule. And how we perform radiation, this particular screening, it is related to the mitochondria. If mitochondrial dynamics or physiology is altered by any molecule, we can use that particular approach for radiation protection. Now, if you look on this particular thing, area where NF-kappa B activation is there, so menon doesn't enter in the cell, it interacts with the TLR receptor, it is toll-like receptor 4. So we have used different type of cell line along with the changes in the expression pattern of NF-kappa B and the mitochondrial dynamics or physiology. So if you look on this particular, even though it is showing a 47.98, we did this experiment more than 20 times and we have complete values about its change, the changes in mitochondrial physiology or mitochondrial membrane potential along with the free radical generation following different time point. Like if you look on this control, near about 48% cells are available in this particular gate. And when we treated with the menon oligosaccharide just after 15 minutes or 30 minutes or 1 hour or 2 hour or 4 hour, if you look on this one, there was transient decrease in mitochondrial membrane potential. Along with the transient decrease in free radical generation was also there. If you look on this one, from 17% it was there up to 11%, and in the between near about 2% cells were showing this suppression of basal metabolic activity or BMR of the cell. So if we look on this particular time window and expose the cell with the radiation at this particular time, we have better chances of radiation protection. And these cells are normal cells. And we did that thing and we have found radiation protection following with the treatment with the menon oligosaccharide. So this work was again reconsidered as whether really mitochondrial membrane potentially or free radical generation is really playing a major role in giving radiation protection by menon or not. We use different inhibitors for the that can inhibit the mitochondrial electron transport chain, either it is rotenone A or antimycin. And then we have identified, yes, it is equally important that mitochondrial functional integrity is very much important for getting radiation protection by the menon oligosaccharide. And same thing was also assessed by expression of various proteins which are related to the mitochondrial dynamics, either it is fusion or fission related protein. So this work was published in BMC Cell Biology. Now it is BMC Cell and Molecular Biology, and also in case of research report that has good impact factor. Now I'm coming to the next part that is related to the high linear energy transfer radiation carbon ion beam, and I'm going to share how this beam is really important for all of us. I think in Southeast Asia, this is the only facility where we can go for cell culture related issue and in how radiation exposure can be done. So we have a cassette in which plates, the cells are seeded, and now these plates are picked by the robotic arm. These plates, it is filled with the media, a robotic arm that comes from the top, and it will pick these plates, and then it is exposed with the carbon ion beam. So this radiation exposure at a particular dose can be done using this particular facility at the Aspire that is available in IUSC, Delhi. And we did various assays following exposure with the carbon ion beam. Either it is nitric oxide generation or free radical generation or changes in mitochondrial membrane potential along with the changes in mitochondrial mass. Yesterday, Dr. Sutupa, she shared the changes in mitochondrial membrane potential with respect to the cell cycle progression. An important thing is that identifying or assessing the mitochondrial mass is equally important. Then only we'll be able to tell that actual fold change or changes in mitochondrial membrane potential is there or not. So these things can be done as per the requirement. And then we use different cell line, either it is normal kidney epithelial cell or transformed cell, and both showed the changes in the mitochondrial mass with respect to the different radiation doses and different time points. And we did the survival studies. This is studies that is clonogenic assay, and we have found that yes, menon can protect the cells, normal cells specifically, from highlight radiation also. So this study was completed is completed with the both type of radiation, either it is gamma radiation or high linear energy transfer radiation. And you can see the relative biological effectiveness with respect to normal cells as well as transformed cells. It is very much different and significant with respect to the radiation. And this survival studies was also performed using sulforhodamine B uptake assay that is related to the positively charged amino acid which are available or histone protein which are available in the nucleus, along with the changes in mitochondrial mass. We all know about the availability of calcium ion, which are very much responsible as soon for the apoptosis or cell survival. As soon as they are released or leaked out from the mitochondria or from endoplasmic reticulum, various endonucleases are activated. At the same time, the mitochondrial matrix or sequestering availability of calcium ion in mitochondrial matrix balance the charges across the inner mitochondrial membrane, and ATP production is equally important in case of radiation protection. So what we found that changes in mitochondrial calcium ion was also kept at the normal level or near to the control level by treatment with the menon, following treatment with the menon. So mitochondrial electron transport chain complexes and how optic atrophy 1 protein is important in relation to the dynamics or movement of electron from one electron complex chain to other electron transport chain complexes. It is important. If the gap between different electron transport chain proteins is increased, or the fluidity of inner mitochondrial membrane because of oxidative modification is increased, there will be more leakage. So if you have suppression in basal in the free radical generation as well as membrane potential, you have better chances of radiation protection. So we have hypothesized that the menon oligosaccharides suppress the mitochondrial activity transiently, and that gave us best possible advantage to get the radiation protection in a particular time window. So this molecule can be used by the rescuers or those who are going to be going to enter in the radiation area or radiation field. And we all knows it is considered as a safe, so it can be taken at any time, any moment by each one of us or any one of us. And how calcium ion is regulated by menon oligosaccharide, that is easy to understand. At the same time, the mitochondrial membrane potential was also observed, that changes in radiation-induced mitochondrial calcium ion was inhibited or reduced by menon oligosaccharide or menon even up to 72 hours. So this was the kinetics study for both membrane potential as well as the changes in the calcium ion level along with the ATP or ADP changes within the cell following treatment with the radiation or different type of radiation, and its control or regulation by the menon oligosaccharide, that is TLR4 agonist. So all signaling is coming from the TLRs to the mitochondria or from TLRs to the nucleus. How it is reaching, that we are trying to understand that how receptor is this, as soon as it ligates, menon ligates with the TLR4, how the signal comes from the TLR4 or from the membrane, biological membrane to the mitochondria. Even though we tried our best, but till date we could not identify how this signaling is reaching to the mitochondria. And now if I want to conclude or summarize this particular work, the menon oligosaccharide provides radiation protection to the TLR expressing cell only. If we use TLR null cell, there will not be any radiation protection. Though in vivo condition is completely different. We have both TLR expressing as well as non-expressing cells. Menon doesn't get absorbed by our body. Because it cannot be digested by our digestive enzymes. So it interacts with the TLRs which are available on our GI tract. So at the same time, if it can be digested by or metabolized by the gut microbiome, it creates the acidified environment within the gut. So it is going to be an important part that it won't support the growth of pathogenic microorganisms which can grow or which are more proliferative or growing in case of alkaline or bit alkaline environment. So it reduces the pH, it supports the goblet cells and other cells, mucin production within the GI tract, and then it gives radiation protection. It supports the gut and gut-brain axis or gut-body axis. And I would like to thank our director, Dr. Sudhir Chandna. He was over here day 4 yesterday, and Dr. Avinash Pandey sir. He supported us in IUSC to use that facility and providing all the infrastructure. And of course, my student, Dr. Shweta Sanguri, who completed this work along with the Preetham Samal, who is sitting over there. He also presented his work day 4 yesterday as a Young Scientist Award. And finally, the DRDO, who supported us for fund and providing us all the infrastructure. Thank you so much for. If any question is there, I'll be happy to answer.
We can take one brief question if anyone is having. Yes, Dr. Pandey.
So this calcium changes in mitochondria, I think is shown by gamma radiation. Have you also studied in case of carbon ion, or what happens to whether there is a differential effect of high LET in terms of calcium ion changes in the mitochondria?
Yes, we did that data I showed.
Okay.
The changes in calcium ion by using fluoro-3 AM dye.
Okay.
So both bound form as well as free form of calcium ion was measured.
But that is by carbon ion or it is by gamma?
With the gamma radiation also we did, with the carbon ion also.
Carbon ion it is getting
yes.
more enhanced, or it is same?
It is, by treatment with the menon oligosaccharide, it was almost near to the control after 24 hour or 48 hour, depending on the radiation dose. But in case of radiation, it was almost 3 to 4 fold higher
calcium ion availability because of fusion and changes in fusion and fission dynamics of the mitochondria. So mitochondria gets enlarged after radiation exposure. So it depends on the time, it depends on the radiation exposure or radiation dose also. Okay, thank you, nice work. Thank you, sir.
Okay, thank you, Damodar. for
Thank you,
very
sir.
nice talk. Yes, okay, go ahead, please.
Just a very quick question. So you showed that mitochondrial fission and fusion, is it LET dependent? Means is it found only for the high LET radiation carbon, or it is found in the gamma radiations also?
It is there in case of any kind of stress. So mitochondria, either they fuses or fission is there as soon as we are exposed cells to the stress. So mitochondria try to repair and support the cell by fusing, so that ill effect or any damaged mitochondria or damaged biomolecules are there. So by fusion, like mitochondrial DNA, if one mitochondria is ill, other mitochondria gets fused with that one, and then these healthy DNA will be with the ill DNA or damaged DNA, so it will be replaced by the healthy DNA.
So have you checked any difference between high LET and low LET?
Yes, it is done.
It is there.
Yes,
Difference is there.
100%, it is there. But depends on radiation dose as well as time.
Okay,
Thank you.
Damodar.
Thank you so much, sir.
Thank you. Now we conclude this session, and I request Amit to come on the dais for some activities related to journal.
I'm going to take hardly 4 to 5 minutes, and thank you very much to accommodate this important thing. On behalf of Society for Radiation Research, we would like to felicitate some of our overseas speakers who physically could not come to our previous meeting, 5th ACRR in Mumbai, but they have made an online presentation, or in fact they have booked their tickets. They were seeking the ME clearance, but due to some of the regions they could not physically present in our meeting. So on behalf of SRR, we would like to felicitate our those esteemed guest, and also SRR would like to express their sincere thanks to the organizing chairman of this meeting, Dr. J.K. Singh, as well as his right and left hand, Dr. Sachidanand Behra. So I would request the founder president of SRR, Professor K.P. Mishra, to please grace this occasion and present that souvenir to some of our guests. So may I request Professor George Iliakis from University of SC in Germany, who has been one of the a very close and intimate member of SRR family now. And Dr. J.K. Singh, please. Yes. And Dr. Sophie Dobias. We have discussed this, so please join us and thank us. And Dr. Prabodh Mehar, who has been contributing immensely to the activities of SRR. Dr. Prabodh Mehar from Sweden. And Dr. Sachidanand Behra also, please join us. I hope he's there around. Please come. And Prabodh Mehar, if someone can help us in finding him out, if he's busy somewhere. And yes. So, and from this side, from the host of 5th ACRR meeting in Mumbai, I would request Dr. B.N. Pandey, who had joined in organization of 5th ACRR as the organizing secretary. I was serving as a convener. So please come. Yes, please come. Yes. And yes, Nina, you please join us. Yes, we all, as a team, we could successfully organize the 5th ACRR. Yes, thank you very much. And Yes. Nina? Yes, please come. So, would request Dr. Mishra to open this souvenir and present it to Dr. Iliakis. Yes. So, what we did, actually, if you see on the back side of this t-shirt, we have printed 3 radiation protection models. Yes. Yes. Yeah. Dr. Mishra for. Yes. Yes. Dr. Mishra, this is for Dr. Sophie. This time, this is the. Yes, you could join. Yes. Yes. Dr. Joe. Just by, you know that the human mind is prone to make errors. So if is there any overseas guest in the auditorium who could not come to 5th ACRR, but it's present in the auditorium? So please join us without any this. I think we are not making any, yeah. Please. Yes. Thank you, sir. Thank you, Dr. Mishra, to accept our this. Yes. Yes, Dr. Mehan, yes. Thank you very much, and I think I leave to the yes.
Thank you, sir. Now we'll take a short tea break, and we'll resume around 11:45 a.m.
A very good afternoon, everyone. Now, we shall proceed with the next session. Bystander effects and low-dose radiation biology. I request Professor Hans Kreis, University of Amsterdam from Netherlands, and Professor Amit Kumar, Secretary of BARC, to chair the session. Sir, kindly introduce the speaker.
Yes, thank you for the kind introduction. Welcome everybody to this last scientific session, bystander effects and low-dose radiation biology. And the first speaker of the session will be Professor Yo of the Korean Atomic Energy Research Institute, who will deliver a presentation on radioprotective effect of new herbal composition MH30 and its supplementary effect for cancer, radiotherapy and chemotherapy. The floor is yours.
Thank you very much, Chairman, and organizing committee members and
all of you participants. Oh, yeah. I come from South Korea. I studied radiation and immune system damage for 30 years more. And then my talk is today my talk is radio protective effects of a new herbal composition, MHC30, and its supplementary effect for cancer radiotherapy and chemotherapy. Here? Okay. My talk is two-part. First is the development of radioprotective herbal product Hemohim, and Hemohim is approved as an immunomodulatory functional food from Korea FDA. And second part is development of modified Hemohim MH30 and ongoing research for approval of MH30 as a supplementary drug for cancer therapy. I think that for really body protection from irradiation, especially lower level than intermediate dose, I think that for that I had to develop an herbal composition with three activities. Have three activities. One is protection of self-renewal tissue and hematopoietic system, and also immunomodulation is required for the natural product simultaneously. So I use a irradiated animal model and cell model. And I screened traditional herbal preparation and herbs, and then try to make a new combination for synergistic effect. As that result, I decide a mixture, new combination of three edible herbs, Angelica, Conidium, Japonica. And then we make hot water extract, and then divide it into two parts. From one part, polysaccharide fraction. Ethanol insoluble polysaccharide fraction is obtained and added to the other part of the hot water extract, and then made Hemohim. So chemical component, maybe about 40% is polysaccharide, and in the other part contains several antioxidant polyphenols, like here. This is, we identify the structure of a major polysaccharide as modified type 2 arabinogalactan. Here, animation. Okay, and confirm the biological efficacy in irradiated mice. Hemohim showed bone marrow stem cell protection and recovery of white blood cell, like here, and protection of self-renewal tissue crypt survivor, like here. And we observed the immune cell activity restored by Hemohim, like here, T cell activity and NK cell activity. And we observed we observed Th1 and Th2 immune response, and after irradiation, Th1 immune response is decreased right here, but hemohim is modulated here, and especially Th2 immune response is increased here, very, very dramatically increased, but hemohim decreased to near normal level. So we focus on the hemohim modulate Th1 and Th2 balance. So we focused on the IL-12 excretion. So we observed that the IL-12 heterodimer expression is like here, depressed by irradiation, and the hemohim restored near to normal level. And then that is almost in irradiated animal model. So approval of hemohim by Korea FDA, we added some research. Restoration of immune response in immune depressed mice treated by cyclophosphamide, and second is immunomodulatory effect in sub-healthy volunteers, and third is immunomodulatory effects in mechanism in aged mice, old mice. And then on the basis of the investigation result, hemohim approved as an immunomodulatory functional food from KFDA, and commercialized from 207. Okay. And then I think that for more supplementation of cancer therapy, in that case, fast-soluble polyphenols is more content. So we added a new production process, 30% ethanol extraction. So as you can see here, firstly, ethanol fraction, and then hard water extraction. And from hard water extraction, polysaccharide fraction is obtained and added this year ethanol fraction. So fast-soluble polyphenol content is higher. So in HPLC profile, you can see here many polyphenol, fast-soluble polyphenol peaks, and especially in decushin, 9-fold here. And then in vitro assay, MH30 reduced the hydroxyl radical like here more than hemohim. And in animal study, we confirmed the radioprotective effect of MH30. This is bone marrow stem cell protection, like here in spleen colony assay, and we observed the bone marrow cell MH30 decreased the bone marrow cell apoptosis, like here. And we observed the Sorry. Slide, please. Slideshow, please. Yeah. MA30 protect the self-linear tissue crypt, like here, more than hemoheme. And in 30-day survival data, MA30 shows about 8% of survival rate, like here. Hemoheme is here, and MA30 is here. And I would like to cancer cell model in vitro. I'd like to skip this slide, and animal study. I introduce animal study. This is breast cancer cell implanted mice treated with local irradiation. Local irradiation. Yeah. Okay. Local irradiated and MH30 treatment like here. And then we observe the tumor cell growth is inhibited by MH30, like here. And yeah, I would like to skip this. And yeah, melanoma cell implanted mice and then treated with cisplatin and MH30 treatment like here. And also tumor growth is inhibited by MH30 like here. At that time, immune cell activity is restored by MH30 like here, NK cell activity, and cytokine secretion is also restored by MH30 here. And next, the breast cancer cell implanted mice treated with paclitaxel and MH30 like here. And then we observed tumor growth cell inhibited by MH30. And next model is lung cancer cell implanted mice treated with cisplatin and MH30 treatment like here. And then we observed the tumor cell growth inhibition like here. And especially I interested in the cisplatin-induced toxicity. So normal mice treated cisplatin 3 times, 3 cycles, and MH30 is treated like here. And then we observe the body weight. Cisplatin is body weight decreased like here, but MH30 modulate the body weight like here. And in kidney toxicity assay, BUN and CRE parameter is increased by cisplatin group and reduced the toxicity by MH30 like here. And kidney weight is decreased by cisplatin like here, but MH30 is restored to the stage. And in histological immunization, we observed the toxicity reduction. And in liver toxicity assay, AST and ALT also increased by cisplatin treatment. By MH30 is decreased near to normal level, and also ALT. And also liver weight is slightly decreased by cisplatin, and MH30 is restored there. And in histological examination, MH30 showed lower toxicity. And we observed toxicological safety in genotoxicity test, rodent acute dose oral toxicity test, and rodent 6 months repeated dose oral toxicity test. No toxicity was observed all tested dose of MH30. So this is slide human cervical cancer cell line, HeLa cell, treated cisplatin and MH30. MH30 inhibited synergistic inhibition of tumor cell growth, but I could not make animal model for cervical cancer cells because mouse cervical cancer cell is only in China, but I cannot obtain the cell line, so I have no animal model. And from these results, MH30 is have a IND, clinical protocol phase 2B approved in 2017. Subject is uterine cervix cancer and uterine body cancer. Because I wanted to have a clinical study for the uterine cancer, because uterine cancer is a major cancer for the radiotherapy in Korea. Okay, so I will try make a clinical study of MH30 on the supplementary efficacy in anti-cancer therapy of uterine cancer patient. Second is breast cancer patient and lung cancer patient. These three cancers are major subject of radiotherapy. In discussion, MH30 have many complex compound. So, excuse me, and some component devoted to free radical scavenging, and some component devoted to animal cell immune cell stimulation and cytokine secretion. So I think that complex compound is more efficient to my purpose. Okay, I would like to acknowledgement for my colleagues and the collaboration team, and thank you for your attention. Thank you very much.
Thank you very much for this wonderful presentation. In view of the issues with the time, we will in this session not permit questions. If you want to ask questions, then please do so in the lunch after conclusion of the meeting. Thank you very much.
Okay, thank you very much. Okay.
Yeah. Thank you, Dr. Chris. Our next speaker is Dr. Perumal Venkatachalam, from Sri Ramachandran Institute, Chennai. Please come on to the dais, the podium. And I would like to tell you Dr. Venkatachalam has worked with a well-known radiation biologist, Dr. Edward Azam. So I think this much is just sufficient about his introduction, and he's one of the best radiation biologists in India. So please. And I would request timer, can you set it at 17 minutes? So that we will also have the time for one or two questions. Thank you.
Good afternoon. My presentation is on radiation exposure from medical imaging and its biological significance. I think last 3 days we are hearing about a lot good and bad effects of ionizing radiation, which is extensively used for varieties of application. However, the use is based on risk versus benefit. So the X-ray, which is extensively used for varieties of medical application, maybe for conventional X-rays, which is used for conventional X-rays, CT, which will give the 3D image, or it can be used for interventional neuroimaging, which will give the used for therapy as well as a diagnosis, PET-CT, which will give the information about metabolic condition or extent of metastasis of a tumor, and nuclear medicine procedure also, which is used, and the X-ray is extensively used in terms of clinical radiation therapy. So the dose received by the human beings during these different procedures varies from few millisievert to in the order of gray. We are talking about low dose as well as in high dose, and it may result into the different health effects. What is the sequence of events? When radiation passes through the thing, it will interact, transfer the energy to the living molecules. It initiates the chemical reaction, photoreaction, Compton effect, or pair production. It will transfer the energy within few seconds. Then it releases the free radicals. In turn, those free radicals are act on the living system or exposed system, in turn trigger the chain of reactions. So this is what I mentioned as a physical, chemical, as well as a biological. Here, the ultimate thing which you are talking about is a biological effect. And the health effects of radiation exposure are classified based on 3 effects. One is the dose, whether it can be stochastic effect or deterministic effect based on the threshold dose, or period of latency. Suppose I am exposed today, how many years I have to wait to see those phenotypical changes or disease condition. That is acute or delayed effects. Third category is depending upon the cell, whether it is a somatic or hereditary. So my question is, okay, we are talking about so much where you and me are receiving the radiations. Suppose we are sitting inside the auditorium, we'll get a chance to expose to radiation, and what would be the dose you and me will receiving it. I think everybody will agree with the concept. The fact about ionizing radiation is we don't know where it is present, which direction it comes. Like a COVID, everybody are exposing every day, right? Then what happened? This is the sources of radiation exposure for you and me in everyday our life. That is from the natural sources, which comes about 85%, whereas remaining 50%, that is a 1/5, comes from the artificial sources. So here we are talking about the average annual background radiation exposure as per the Icrr, which is 2.45 millisievert per year, which will vary from country to country, or again depending upon what type of medical examination which we undergo. Okay. So we are talking about the low dose. How to define low dose? It will vary from radiation protection as well as in radiation therapy. If a patient undergoing radiation therapy, 2 gray may not be the low dose. But in terms of radiation protection purpose, as per the ICRB, this is a definition, that is acute doses of less than 100 milligray is considered as a low dose. That is what Dr. Amit also was mentioning. If it is, exposure is less than 100 milligray, what happened? Whether the effect will be additive or supralinear, whatever it is, there is a huge debate is ongoing. So that is what we wanted to generate a data on these low dose aspects. So experimental model available to test the hypothesis whether low dose can induce those biological changes. It can be from in vitro studies. We can use cell lines. Unfortunately, we'll be talking about whether the cell line can relate the human beings. Species to species variation, most of the journals are, cell lines are animal in origin. And we can do for the animal experiments. I think those who are working with the biological sciences know the challenges involved in conducting experiments using animal models, because getting an IEC approval is much more challenging than doing with research with other things. Epidemiological studies from natural high background radiation, that everybody will not having the chance to collect the sample. I think next presentation will listen from Dr. Vivek Kumar about this epidemiological data. And since I am attached to that medical hospital, though we have a good radiology department, got an opportunity to collect samples from the patient who are exposed to radiation as part of the therapy. Okay? So this is what typical doses received by the patient during the various X-ray or ionizing radiation based imaging as well as in diagnostic modality, which will vary from 0.02 millisievert as well as a cancer patient undergoing radiation therapy. The total tumor dose about 50 to 60 gray of fractionated radiation exposure. Had an opportunity to collect the blood sample from the patients undergoing all these procedures. Okay, undergo all these procedures. Then coming to the radiation protection, if you take the sample from the patient who already undergo PET-CT or radiation therapy, remember their genome is already unstable. Over and above, if you are going to expose to the radiation, take the sample, it may not be able to reflect the real scenario. So in that sense, we can take a subject, sample from the subject who undergo for the imaging for other modalities who are all not patient or known any altered conditions. Okay, so that is why we have taken the samples. So the study participant, which will vary from patient undergo radiation therapy, nuclear medicine procedure, X-ray based imaging for mammography and cone beam CT. These two are the data for today's presentation in my thing. Okay, so these are all the biomarkers which we have experienced. We are using it. I think last 3 days we are listening to this biomarker. First one is the gold standard marker, that is a dicentric, which is ionizing radiation specific. Then we can use about this micronucleus. Somebody was asked a presentation, which is a rapid assay. This H2X assay, we can measure the damages immediately after the exposure, because here you have to culture the cells for 3 days, 4 days, by the time the damages can get repaired. Whereas if you use this assay, immediately you can measure it. And if it is a high dose, you can use for the premature chromosome condensation. And we are talking about the gene expression. I am surprised there is no presentation on miRNA. This also, there is a milestone paper appear in the Science, which has the potential for radiation biodosimetry. That also we are working on it. Anyway, coming to the results. So initially we started the experiment with the cell lines. That also we wanted to mimic with the in vivo condition. That is what we grow the cells in the 2D as well as the 3-dimensional architecture. In terms of the cancer patient sample, we are talking about the 3D organoids. Whereas here it is a primary cells, they do not have the property of growing like an organoid. So we can grow the cells in the 3-dimensional architecture. Then the cells were exposed, co-cultured with the unexposed cells. Then we studied different biomarkers like a micronuclei. This was because of the rapid assay we have used it. So here this is a control cell. The cells are exposed to 20596 milligray per centimeter square. This is the typical dose range received by a person when he or she undergo conventional X-ray based imaging. Since our in vitro results with the cell line induce the DNA damages significantly, that too the 3D showed more images compared to, that is a high levels of DNA damages compared to the two-dimensional culture. Then we extended the study to the patients who undergo different type of imaging. So here we have taken the sample from the subject undergo computer tomography imaging, PET-CT imaging, PET alone, as well as a computer tomography. So this one is a different range of effective doses registered in the machine. So effective doses vary from 2.35 millisievert to 63.36 millisievert. Remember, the dose received by the patients are below 100 millisievert. However, if the procedure is repeated or a new investigator is trying to do the scan, he can move the scan up and down repeatedly. That time the patient can get accumulated more than 100 milligray. Okay? So that was the time. Then we also did with the PET-CT. So these are the physical doses of, the range of physical doses. You must be wondering what is the big deal in measuring the doses alone. Also, we require to have a biomarker. So here, this one is a DAP. DAS is nothing but is a dose area product. Patient undergo interventional neurology imaging. There also it is a X-ray based procedure. So this dose is represented as a DAP versus the fluoroscopic time. As dose increases, there is an increase in the accumulation of the DAP dose. Also, we have, these are the comparisons of the, we also kept the TLD to measure the dose at the different location, because there is a literature, low doses can increase the risk of leukemia as well as in thyroid cancer. So we are concentrating on the dose estimation to this region of the eyelids as well as in thyroid by keeping the TLD, measure the dose. Because when you measure the dose with the patient, which is an overall dose, not the dose at the surface, so we measured that one also. Then we extended to find out the correlation between the accumulated dose versus the dose versus the biomarker. So this one is a gamma H2X assay. First we did with the flow cytometry, which is a quantitative measurement, not qualitative. Then we have extended the study using the micronucleus, because here, which is considered as a relatively stable damage or late marker of DNA damage compared to that of H2XA. Here also we observed a significant increase in the micronuclear frequency. Then we also extended to the gold standard chromosomal aberration assay also. Here also you see the cancer patient, after the PET-CT, there is a significant increase in the chromosomal aberration frequency. This is how we have confirmed that patient undergo low dose radiation procedure. They receive significant amount of radiation doses also, which can induce an early as well as an late DNA damages. Then we extended the study, because as already mentioned, these are the patient undergoing a PET for the staging or other kinds of procedure. We extended here for the nuclear imaging, that is patient received iodine 131 as part of the imaging, and high dose it is for the therapy. We also collected the samples from mammography. Nowadays, a woman at the age of 40 are recommended for annual master health checkup. Actually the mammography is a routine examination procedure. If you undergo rotated frequent procedure, there can be accumulation of the dose. So that is why we are interested to do that one. Then also another thing is called as an cone beam CT, which is extensively used in especially for dental applications, especially for cosmetic applications. So we have taken the blood samples from the subject. This is what the person received an iodine 121, 25 patient, the injected microactivity, injected radioactivity vary from 3 millicurie to 4.5 millicurie. Then these are all the gamma H2XA foci frequency, that is an early marker, we have mentioned it. So there is a significant increase in the H2XA frequency immediately after the imaging procedure. We also done with the micronuclear frequency, which is a residual marker of DNA damage. In the iodine 131 scan, where the injected activity is only 4 millicurie, here also there is a significant increase, whereas the patient treated received iodine 131 as a therapy, that is for toxicosis, there is a significant increase and retain in the levels of micronuclear frequency. Remember, here they are undergoing as part of the treatment, and we also extended the thing for the chromosomal aberration for the same marker. There is a significant increase in the levels of chromosomal aberration also. Then after completing this one, we have extended the study for mammography. Here also we have done the 23 subjects. So here also the marker we have used it is an for H2XA as well as an micronuclei. Morning in the there is a one of the presentation we listen. There is an inter-individual variation. The light line is before the procedure. Dark line is the after the mammography procedure. Even the baseline frequency of micronuclei are after the mammography, which is not uniform. There is a heterogeneous levels of baseline frequency itself. Also it differ from after the mammography. And we also measured the micronuclei because which is a residual damage. And we also extended, this one is the relationship between the average glandular dose, that is the dose accumulated in the breast tissue, and we measured the correlation between the H2X frequency as well as in chromosomal H2XA glandular dose. There is a positive correlation, whereas when we are trying to measure the residual damage, that is a micronuclei, there is no no correlation. It suggests the induced DNA damages can get repaired. It may not increase the risk for any late effects. We also extended the study for cone beam CT, which is extensively used for cosmetic application. Here also we have taken the samples, measured the H2X assay. You see there is a significant increase in the frequency of gamma H2X assay. Also we have done for the micronucleus. Here also there is an increased frequency of the micronuclei, but the level is not statistically significant. So the data we have submitted, which is in the review process, and once we observed the chromosomal aberration, how to relate it to the long-term effect, we also measured the gene expression of these things. Actually, there are 4 markers which we identified. One is called as that is a CDKN1A, and DDBR2, FDXR, PCNC. These are all the genes involved in the deciding the cellular response upon radiation exposure, that is checkpoint activation, DNA repair, or apoptosis. All the things suggest there is an altered levels of gene expression, but ultimately what I wanted to convey is the medical applications of radiation is based on the risk versus benefit. So as a patient, when he undergo for the therapy or imaging procedure, definitely the advantage gained by the subject is much more higher than the risk associated for the cancer development or other things, and the models it can be used as an information to examine the health effects of low dose ionizing radiation. So this is a place where I am coming from. So my sincere acknowledgement to the funding agency, AERB, as well as in SPARC, my scholars who have supported to generate the data, and of course my institution, Sri Ramchandra Institute of Higher Education and Research, and of course the opportunity for Society for Radiation Research, as well as in the organizer given the nice opportunity to share some of my data. Thank you so much.
Thank you very much for this very clear presentation. Like I said, there may be people with questions, but that will come after this session. We now move on to the third presentation within this session by Dr. Nina Shetake from the Bhabha Atomic Research Center in Mumbai, who will talk about tumor-targeted nanoparticles for magnetic hypothermia-mediated enhancement of cancer chemoradiotherapy investigations. You have the floor.
Thank you for the kind introduction, sir. Good afternoon, everyone. I am Dr. Nina Shetke, and firstly, I would like to thank the organizers for giving me this opportunity to share some of my research work here among the eminent scholars. Today, I'll be sharing some research related to development of a doxorubicin encapsulated targeted nanoparticle for multimodal therapy application, and also for mitigation of the side effect of doxorubicin therapy, that is cardiac toxicity. So, as all of you are already aware that chemoradiotherapy modality, it is one of the most widely used treatment modality for solid cancers. But one of the limitation of this therapy is that it is not very cancer cell specific, hence the associated side effects. So here nanoparticles, they can help to overcome this limitation because they can be designed into targeted drug delivery vehicles. Why so? It is because of their specific biophysical properties like high surface area to volume ratio, because of which we can functionalize them with some targeting moieties which can make them tumor specific. And also the chemotherapeutic drugs which are encapsulated in these nanoparticles, they show improved pharmacokinetic properties and also reduce normal tissue toxicity. So if we look at the trend from the past 20-25 years, we can see there is an increasing number of publications in this domain. At present, in clinical trial, there are around 45 such nanoparticle-based formulations for anti-cancer application, but only 11 so far have been approved for clinical use. Now, why this low translation for lab to clinic? I would like to attribute this to two major factors. One is the biological barrier. That is, once this nanoparticle enters into the system, how efficiently it is able to escape the RES, that is detection by the reticuloendothelial system. It will determine its efficacy, and also once it enters into the tumor, its intracellular uptake into the cancer cells and its ability of the active component or the drug to reach its intracellular target. Like in case of doxorubicin, its potency is maximum when it intercalates into the DNA. So all these parameters will govern the efficacy of the nanoparticle. Apart from this, there are certain pharmaceutical barriers also associated with it, like maintaining the batch-to-batch variation during large-scale production of the nanoparticles. And this nanoparticle should have a favorable toxicity profile for them to be considered as an alternative to the already available chemotherapeutic drug. So here we have tried to develop a nano delivery system for doxorubicin therapy. Now in case of doxorubicin, if you see, the plasma half-life of the pure drug is just 30 minutes. So there is a very little accumulation in the tumor cells, and it is associated with mainly cardiac toxicity and toxicity to the liver and the kidneys. In 1995 itself, the first liposomal formulation of doxorubicin it received the FDA approval, which is called as Doxil. It significantly improved the plasma half-life to around 54 hours, because of which there was a significant decrease in the toxicity that was associated with these organs. However, still there is a scope to enhance its efficacy. It's mainly because if you see here, this liposomal formulation, it is passively targeted to the tumor. So in spite of it being able to deliver more drug to the tumor, the clinical trial data showed that the efficacy of lipodox was not better than the free doxorubicin. And also the mechanism was not that well understood why this is happening. So we thought we should work on this problem and try to improve the targetability as well as the efficacy of this liposomal formulation. So we came up with this targeted formulation called as TLMD, wherein we first optimize the composition of the phospholipid so that we achieve liposomes less than 200 nanometer. This is the ideal size for RES uptake and the passive targeting of the liposomes to the tumor site. We functionalize them with the polyethylene glycol spacer. This improves their blood circulation half-life and also enables passive targeting. For making them cancer cell specific, we functionalize them with cyclic RGD peptide. Now this peptide, it enables binding with its specific receptor, that is alpha-5 beta-3 integrin receptor. This receptor is expressed on several solid cancer cells and also on the tumor neovasculature. Then doxorubicin, because of its hydrophilic property, we encapsulated it in the core region of the liposome. And as I mentioned, we wanted to improve the chemotherapeutic efficacy of the entire formulation. So we trapped magnetic nanoparticles, MNOA, in the bilayer region of the liposomes. Now the advantage of iron oxide, it being super paramagnetic, it's a very good theranostic agent. You can use it as an MRI contrast agent for diagnosis. Apart from that, in presence of AC magnetic field, it can generate hypothermia. So it's a very good magnetic hypothermia agent. And some of our preliminary studies in the lab showed that this iron nanoparticles, they can interact with the intracellular chaperone proteins, specifically HSP90, and sensitize the cells to subsequent gamma radiation therapy. So keeping this preliminary data, we designed this formulation called as TLMD. We first characterized it for its different biophysical properties. So cryo-TEM imaging, we could see the synthesis of spherical liposomes. Around 70% of the population was unilamellar, and the encapsulation of doxorubicin is visible in the form of high contrast lines, which are present in the core region of the liposomes. The iron oxide high contrast was visible in the peripheral region of the liposomes, which supported the design that we intended to make. This is the cryo-TEM image of lipod, where you can see that the liposomes show the encapsulation of doxorubicin in the core. So we determined their size by TEM as well as by dynamic light scattering, and we got the desired size of less than 200 nanometer. Its average size is around 170 with a very narrow polydispersity index of 0.2, suggesting that it's a quite narrow size distribution population that we have achieved. And zeta potential analysis suggested good colloidal stability of this formulation with a slight negative charge. We also measured the encapsulation of the drug in the core and the bilayer, that is for doxorubicin and the iron nanoparticles. And the first step was to check whether indeed the targeting of CRGD offers any advantage in terms of intracellular uptake in cancer cells. So we screened several cancer cell lines for the expression of this receptor. And in human glioma cells, we could see significantly higher expression for this receptor. Then we conducted uptake studies. And here you can see that as compared to the non-targeted liposomes. So these liposomes are exactly same like TLMD, except that they don't have the CRGD peptide tagging. So TLMD offers the advantage of higher intracellular uptake in the glioma cells. We perform the experiment again by pre-treating the cells with a blocking peptide so that the receptor is now engaged. And here you could see that especially in the cells treated with TLMD, there is a decline in the percentage encapsulation. So this supported our hypothesis that indeed that tagging with CRGD, it offers the advantage of receptor-mediated uptake in the cells which are positive for the integrin receptor. We also validated this further by using a specific marker for the early endosomes. This is called as EEA1, which are visible in the form of green foci. So here in the cells you can see that the cells which were treated with TLMD, there is a significant increase in the number of these foci. For doxorubicin also, it showed a similar pattern and it co-localized with the green foci of the endosomes. We performed these experiments in a cell line which shows very low level of expression of this integrin receptor. Here you can see that in control, the endosomes are visible, but the cells which are treated with TLMD, they show a diffuse pattern. So this suggests that there is some non-receptor mediated uptake that is happening in these cells. Then we screened for the anti-cancer efficacy in several cancer cells, and our data suggested that as compared to lipod, which is a commercially available liposomal doxorubicin formulation used in cancer patients, TLMD was found to have more cytotoxicity on the tested cancer cell lines. We further checked for its ability to enhance the efficacy of gamma radiation. So we did clonogenic assay, and here also you can see that as compared to only TLMD, the combination treatment shows a significant decrease in the percentage survival. Since gamma radiation, the major mechanism is induction of DNA double-strand breaks. So we wanted to check what happens when we combine TLMD with gamma radiation. And to our surprise, what we observed that TLMD itself is able to significantly induce DNA double-strand breaks. And this magnitude is further enhanced when we combine them with gamma radiation. So this was also validated by the upregulation of the DNA repair proteins like phospho-ATR, RAD51 and CHEK1, especially in the combination treatment group. Then the second aspect is magnetic hypothermia, as these liposomes have iron oxide nanoparticles. If we expose them to AC magnetic field, they should generate heat. So we checked for their heating ability under AC magnetic field, and we could see that they could reach the hypothermia temperature within 15 minutes. And in cell studies also, magnetic hypothermia offered the advantage of better killing. By Western, we could see that there is an upregulation of pro-apoptotic proteins, and it is also associated with G2M arrest. Now the most important question remained whether this design or these liposomes can perform in an in vivo tumor model. So here we have selected a syngenic model for skin fibrosarcoma, and for real-time and non-invasive imaging, we functionalize our liposomes with indocyanine green. This is a near-infrared dye which is routinely used for angiography. And our hypothesis was that although fibrosarcoma tumor cells, they show a lower expression of the receptor, but the neovasculature is known to have high expression of this receptor. So via passive targeting and targeting of the neovasculature, we expected good homing as well as efficacy of our formulation. So we did intravenous injection of our formulation, and within 15 minutes, you could see a good accumulation of the fluorescent signal in the tumor area. This is the tumor on the leg. And on day 7, we isolated we sacrificed the mice, isolated the organs, and we looked for the intensity of fluorescence, and clearly you can see the intensity is very high in the tumor. There is some background signal in the kidney, but the main off target or the concern of doxorubicin, that is heart, you can see there is no remnant fluorescence signal visible there. This is a quantitative data where you can see that the targeted formulation offers the advantage over the non-targeted one in terms of homing of the liposomes in the tumor site. And we also performed this tumor targeting experiment using another more resistant model. This is an orthotropic triple negative breast cancer model of 41 cells. And here also we could see that TLMD was able to selectively accumulate more in the tumor site compared to the other organs. Now, with respect to efficacy, we perform experiments in the fibrosarcoma model in combination with magnetic hypothermia as well as magnetic hypothermia followed by gamma radiation. And clearly our data showed that the combination treatment is found to be much more effective as compared to only radiation or the lipod combined with gamma radiation. Okay. Now another important aspect, as I mentioned during my introduction, that doxorubicin major concern is the cardiac toxicity. So we have thoroughly evaluated several parameters associated with the heart toxicity. One of the parameter is the level of serum levels of CKMB. This is an early cardiac damage marker. And you can see that compared to control, TLMD does not show any significant change, although it is visible in case of the commercial formulation as well as high concentration of DOX. Histopathology analysis also suggested insignificant changes, but in case of the positive control, loss of myofibrils was visible. We also did specific activity of antioxidant enzymes in the heart tissue lysates, and here TLMD did not show much change compared to the positive controls, where a decrease in the antioxidant enzyme activity was observed. Then a more direct indicator of cardiac toxicity is the cardiac fibrosis. So we did trichome staining, where the collagen deposition appears in the form of blue color. And here also you can see that TLMD does not show much change. And one of the mediators of cardiac fibrosis is phosphosmad3. So the expression of phosphosmad3 was also not found to be changed in the TLMD treatment group. I also wanted to study the mechanism how these nanoparticles are actually inducing cell death. So since these liposomes have iron, we suspected that iron overload might be able to induce ferroptosis. So we pre-treated the human triple negative breast cancer cells with different inhibitors of apoptosis, autophagy, and ferroptosis. And we carried out cell viability assays, and specifically in the ferrostatin group, you can see there is a significant rescue of cell death. And the other biochemical markers of ferroptosis, such as extracellular release of LDH and cell ballooning, this was observed in the TLNB treatment group, but it was significantly rescued by the ferrostatin treatment. Similarly, subG1 cells also suggested that ferroptosis involvement is there. These are electron microscopy micrographs of the cells. Here, one classical feature of ferroptosis is alteration in the mitochondrial shape and size. And here we could see a significant increase in the mitochondrial size, and mitochondrial fusion was visible in the TLMD treatment group. This was also validated by mitotracker green staining, where you can see that the foci size has significantly increased in our nanoparticle treatment group. And ferrostatin as well as deferoxamine mesylate, which is a chelator of iron, it is able to reverse this effect to some extent, suggesting the involvement of ferroptosis. Other important mediator is ROS. So we checked for the kinetics of cytosolic ROS, lipid ROS, as well as mitochondrial ROS, and all of these parameters were found to be upregulated in the TLMD group, and they were associated with increased DNA double-strand breaks. So in short, we can see that TLMD is able to undergo receptor-mediated endocytosis in the triple-negative breast cancer cells, induce cytosolic ROS and lipid ROS, resulting in damage to the membrane, release of damp molecules, alteration in mitochondria, and induction of ferroptosis. At present, we are trying to identify whether these damp molecules can trigger immunogenic activation in these tumor models in mice. And this is a very good carrier, TLMD. It can be used for encapsulation of other anti-cancer drugs also. And we are conducting some toxicity studies in GLP labs so that we can take this formulation further. This is the patent that we received for our formulation. And I would like to acknowledge my mentors, Dr. B.N. Pandey and Dr. Amit Kumar, for their continued guidance. All my lab members, Dr. Hassan, our Associate Director, Bioscience Group, and collaborators from BRC, Actrec, and IIT. Thank you for your kind attention.
Thank you very much. This was a very impressive presentation. Thank you. No questions. We go to the next speaker, Dr. Kumar from the Baba Atomic Research Center in Mumbai, on biological and health effects of chronic high-level natural radiation in humans from southwest coastal areas of Kerala. That is always a nice subject.
Thank you, Chair. Very good afternoon. First of all, let me thank the organizers of this wonderful conference for giving me an opportunity to discuss about the biological and health effects of chronic low-dose radiation exposure in human population from southwest coastal areas of Kerala. So this work is being carried out at Low-Level Radiation Research Laboratory, BRC Kollam, Kerala, as well as at Low-Level Radiation Research Section, BRC Mumbai, under an MOU with the Health and Family Welfare Department of Government of Kerala. So we know that humans in their day-to-day life are exposed to both natural and man-made radiation sources, which has the potential to induce both germline and somatic mutations. And currently, the risk assessment model is the linear no-threshold model based on the data from atomic bomb survivors, and which consider any exposure to ionizing radiation to be harmful, whether it is low dose, high dose, whether it is a chronic or acute exposure. And the linear increase in the risk in the low dose region, especially below 100 milligray as defined by L&T, is highly controversial due to the absence of reliable data in this region. So, however, most of the human encounters with the radiation will be environmental and occupational exposures, which will be largely chronic low doses. So the question is there a risk due to the chronic low dose radiation exposure in humans as predicted by the LNT model? So to address this, we have a population from the high level natural radiation areas which may provide direct evidence of the hereditary as well as somatic effects of ionizing radiation, as these individuals are exposed during all stages of their life for generations to chronic low doses. So among the various high level natural radiation areas, the one in the southwest coast of Kerala is thickly populated with about 4 lakh individuals. The high radiation area of Kerala is shared by 2 districts in the south. One is Kollam and another is Alleppey, and it's a stretch of about 55 kilometer long and 0.5 to 1.5 kilometer wide from west to east. So the black sand present in this area has monazite, and which has thorium-232 and uranium-238, giving varying level of exposure to the inhabitants, making this area a unique natural radiation laboratory to study the biological and health effects in humans. So Karunapalli is the center stage of high radiation area of Kerala, and this is a recent dosimetry study we have conducted and is given as a bubble chart here. And the average exposure in this area, in this taluk, from external gamma radiation is 4 milligray per year. And there are some areas where the levels are up to 173 milligray per year in some of the beach areas. And those areas where inhabitants are getting less than 1.5 milligray per year is considered as normal, and where they are receiving more than 1.5 milligray per year as high radiation areas. So some of the individuals from this high radiation areas is receiving more than 20 milligray per year with a range of 10 to 40 milligray per year compared to the occupational exposure limit of 20 millisievert per year. So this may result in a cumulative lifetime dose of more than 1000 milligray. And another thing is that some of the pregnant women in the high radiation areas of Kerala may receive more than 20 milligray during their pregnancy period compared to the dose limit of 1 millisievert for a pregnant female worker. So this is the scenario we are going to address. So for this, actually we have screened more than the exposure, that is exposure taking place in parents, may induce germinal mutations, and which may result in congenital malformations or birth defects in the form of cleft lip palate, Down syndrome, clubfoot, hypospadias, congenital heart diseases, spina bifida, and a number of other minor malformations. When the exposure is happening during pregnancy, it may affect the fetus or the embryo and may lead to microcephaly, mental retardation, malformation, and embryonic death. So in order to address this, we have screened more than 180,000 newborns, and for a period of 3 decades, and in 4 government hospitals from this both normal and high radiation areas. And the results are analyzed based on the cumulative dose received by their parents. So a doubling of the cumulative dose in fathers below 30 years of age from 33 milligray in normal areas to 82 milligray in high radiation areas, or in fathers above 30 years of age from 41 milligray in normal areas to 102 milligray in high radiation areas, did not increase the risk of stillbirth, major congenital anomalies, or overall congenital malformations. Similarly, a doubling of the cumulative dose in mothers below 25 years of age from 25 milligray in normal areas to 60 milligray in high radiation areas, or above 25 years of age from 34 milligray in normal areas to 75 milligray in high radiation areas, did not increase the risk of stillbirth or major congenital malformations. However, in mothers below 25 years of age receiving 60 milligray from high radiation areas showed a significantly less overall congenital malformations compared to newborns to mothers receiving 25 milligray of cumulative dose. The dose response for stillbirth, malformation and overall malformations did not show any response when the dose in the newborns were categorized based on the parental radiation exposure from less than 25 milligray to greater than 100 milligray. More than 27,000 newborns were screened for chromosome abnormalities as well as this karyotype anomalies, and we found that the dicentric frequency was comparable in both the populations, whereas translocation, the stable aberrations, were significantly less in newborns from high radiation areas. And we did not find any constitutional chromosome anomalies, and that was comparable, both the numeric and structural abnormalities were comparable in both the groups. All the Down syndrome cases were characterized using GTG banding as well as FISH for free trisomy as well as translocation trisomy, and the prevalence of Down syndrome was 0.0767% in both the populations, that is from normal and high radiation areas. So the study inferred that the chronic low dose radiation exposure does not induce birth defects or cytogenetic damage in newborns. No risk of hereditary effects with a paternal cumulative dose up to 100 milligray indicate that the newborn data does not support the LNT model in low dose region. So we assessed the potential of low dose radiation to induce somatic effects in adult individuals using a number of biomarkers, and a 10 times increase in the chronic cumulative dose, that is from 53 milligray in normal areas to 531 milligray in high radiation areas, did not increase the frequency of dicentrics, translocations, total chromosome aberrations, frequency of micronuclei, or frequency of DNA double-strand breaks in terms of gamma H2X. The FISH with the pansyndromeric probes in binucleate cells indicated that the proportion of clastogenic and aneugenic events leading to micronuclei formation was comparable in both the populations. There was no increase in basal DNA damage or oxidative DNA damage in terms of oxypyridine or oxypyrimidine. More than 15 times increase in the chronic cumulative dose in individuals below 40 years of age from 33 milligray to 560 milligray, or in the individuals above 40 years of age from 51 milligray to 961 milligray. It did not contribute to increase in the somatic mutation frequency at the HPRT locus on X chromosome. Further molecular analysis indicated that the deletion frequency was comparable in both the population. Recently we have initiated the nanopore sequencing of the 45 kilobase region, and only few only few samples we could do, and the initial glimpse of results indicated that even with a cumulative dose of 1000 milligray, we are not getting any new mutations at this locus. So in 1990, Regional Cancer Center has established a cancer registry in Karnapalli Taluk, and they did a follow-up in 150,000 individuals between the age group of 30 to 84 for a period of 20 years, and they came out with an excess relative risk of minus 0.05 per gray. A similar study was conducted in Yangjiang, China, which is also a high background radiation area, in a cohort size of 125,000 individuals, and for cancer mortality as well as incidence, and they came out with an excess relative risk of minus 0.11. So the somatic studies indicate that the somatic effects of chronic low dose radiation exposure is not evident in the adult individuals from high level natural radiation areas of Kerala for DNA damage, chromosome aberrations, mutations, and cancer risk. So data from adult individuals do not support the LNT model, and radioadaptive response was observed in individuals receiving a cumulative dose of more than 500 milligray, and which was evident by the reduction in the DNA damage when the samples were exposed with the external gamma dose of 2 or 4 gray. A similar result was obtained for micronuclei frequency when the samples were challenged with 1 or 2 gray, and this also was found in individuals above 40 years of age and with a cumulative dose of more than 500 milligray. Low dose radiation could induce the repair in, enhance the repair in high radiation area samples, as we could see with the gamma H2AX response, as well as we found an increase in the initial repair ratio in individuals from high radiation areas compared to normal. So the microarray data showed that several DNA damage response as well as repair genes were activated in individuals from high radiation areas, and this was further confirmed with the 2 gray of radiation in some of the repair genes. And recently we could analyze some of the data, and we found that there is a difference in the distribution of age at death in individuals from high and normal radiation areas in both males and females when we compared the data for a period of 12 years ranging from 2011 to 2022 in a population of 1,10,000 individuals. And the analysis showed that both the males and females showed a better lifespan in the staying in the high background radiation areas. And generally the females live 5 years more than males. And recently a study in the US population which covered the entire US population of 320 million, and they showed that there is a 2.5 years longer life expectancy in those individuals who stay in relatively high radiation areas due to a decrease in the cancer mortality. And the outcome of these studies says that absence of hereditary or in utero effects in this population, and there is a reduction in the overall congenital anomalies in mothers below 25 years of age, and there are absence of somatic effects in adults. There is no increase in the cancer risk. There is a better lifespan as well as radio adaptation. So we ask a question whether these individuals undergo a healthy aging while staying in these areas. So in order to address this, we have initiated a study in which we compare the biomarkers from individuals of less than 25 years of age and more than 55 years of age receiving a cumulative dose of less than 25 milligray to more than 1000 milligray using immune response, then hematological, biochemical parameters, then multi-omics approach by proteomics, metabolomics, then chromosome aberrations, micronuclei, then translocations, then telomerase study, then whole genome sequencing and transgenerational effects, as well as epigenetic effects in terms of microRNA methylation, histone modification. So we are going to cover the entire biomarkers in this group of individuals. So it will be definitely going to indicate you what are the biomarkers for aging in this population. So this may answer whether they undergo a healthy aging while staying in the high background radiation areas. So this may also help to answer the question whether these individuals' response follow a threshold model or whether it follows a hormetic model of dose response. So I would like to thank our Group Director, Dr. P.A. Hassan, Dr. Santosh Kumar from RBHSD, as well as Dr. Deepak Sharma, and a handful of my colleagues who contributed to this work, and especially to the Directorate of Health Services of Government of Kerala and Chief Registrar of Births and Deaths, Government of Kerala, who provided the lifespan data, then Board of Research in Nuclear Sciences, then technical staff of our group, as well as the participants from normal and high-level natural radiation areas of Kerala, Kollam. Thank you very much.
Thank you, Dr. Kumar, for presenting an very elaborate insight about this important project of DAE. Thank you very much. You finished well before time, and I think for questions, yes, we are going one question, please.
I am a member of HPS USA. You know, I heard that they are going to reduce the limit to radiation worker, you know, to 20 to 10 millisievert. Do you know anything about this?
Pardon, sir, I could not hear your question properly.
You know, those limit for radiation worker, you know, ICRP is going to reduce from 20 to 10 millisievert per year. Do you have any information regarding this?
No, 20 millisievert is the limit which is generally followed, and in India it is 30 millisievert. So you are talking about further reducing it.
Yeah, 10.
Yeah. But I have no comment because the data from our study is based on the chronic low dose radiation exposure, and most of the occupational exposure will be in that category only. So it is a subject of big debate, and several reviews to be conducted before taking
Yeah,
a decision whether the dose limits should be reduced or not.
Yeah.
And we are contributing to that one only, whether these studies can contribute to the real setting the limits.
Yeah, why ICRP is not, recommending, there is no scientific evidence about the low dose, there is no scientific evidence. I worked in Romsar, North Iran, for 10 years, and the same thing, whatever you say, I agree with you, So, but why it is not taking average background radiation, high background radiation, averaging it and keeping it as a threshold?
Yeah, these works are regularly assessed by UNSCARE and all. And
Is it due to ICRP is an autonomous body?
Yes.
Yeah.
So I think, so I think it's good that discussion is being initiated, and please continue.
Yeah, sure.
Thank you very much, Dr. Kumar, for
Thank you,
this.
Chief.
Yes. We move on to the next presenter, and he is Dr. Veom Saxena from Bhabha Atomic Research Center. So, oh sorry, I'm sorry, Dr. Bipan Kumar. Dr. Bipan Kumar Parihar from Naipur, Hajipur. Please come. And yes. Yes.
Good afternoon, everyone.
Thank you.
So first of all, I thank the society to invite me over this podium. So I'm going to present my latest work, what we are currently doing in Naipur, Hajipur. So we have previously published a lot of work on the radiation biology, especially how the radiation causes cognitive impairments, starting from the high LAT from NASA 11 dose to the clinical doses. And we have previously have no doubt that radiation is not good for the brains. And it has structurally, functionally, and endocrinally has changed the brain functions. But the question arises, how it changes. But this question is a part of the mitigating strategy developing, minimizing also the radiation effects. So our current talk only solely focus on the glycolysis and energy metabolisms, because after currently working on 10 to 15 years of radiations, we have found the basic mechanism of radiation is changing the energy metabolisms. The cell got under deprivation totally, and this is caused out of sequential events is happening. So this will mostly focus on the cytosolic energy metabolisms, especially the glycolysis, glucose transports, then mitochondrial energetics, and also how the absorption of glucose to each cell will changes. As you know, the brain is like in Naipur Hajipur, we do not have basic radiation sources. So we have we have used at Mayur Cancer Hospital in Patna. So their physics has done a tremendous job. We have exposed the animal for only cranial radiations, head only radiations. It was 9 gray, 1 gray per minute was given. And we have properly taken care that the rest of the body is shielded. So the head, the spill dose was 0.33 milligrays. So there was a little bit spill was there, that was not only in the rest of the area, but most of the body was completely prevents. So animals were exposed by 9 gray. They waited for almost 1 month, waited for a week, then drug was given. So I'm not going to part of the drug part and the behavior part, only molecular mechanism data will be presented in the studies. And then we have analyzed how the animal behave in the learning and memory. And we find out the molecular mechanism, neurogenesis, glucose transporter, neuronal circuits, inflammations, and all animal function was done. So what we have done first, we have done the next generation sequencings. We found 7,000 genes were changed. But what is the significant related to our brain function and glycolysis? Yes, we have identified there are nearly 23 genes. We are basically upregulated, and now 111, so they are down-regulated. So most of the genes, we are only focused in the cognitions. Just like this gene is an NPS is an energetics mitochondria on the Moji cells. Moji cell is a special type of brain cell which acts as a nursing cell. You know, brain is millions of neurons. Each neuron has specific parts. And this gene is specially involved in the hippocampus formation of new neurons, because 90% of a brain is post-mitotic. Only 2% cells are formed every day. So there's a lot of nursing cells. Nursing cell, basically when new cell is born, it maintains that. And we found the significant decrease of this gene has been gone down. And this drastically can change. Secondly, the mitochondrial ATP8 and mitochondrial cytochrome B, this enzyme has been downregulated. Other than that, a lot of sequential changes has been observed in epigenetics changes, especially the SZ2, TAT1, TAT2, TAT3. But TAT1 has found most significant. This enzyme or gene has been clearly related to the cognitive flexibility as well as cognitive rigidity, and also the forgotten the bad memories. That's the reason one of the patients who go for radiotherapy, they are not able to forget the past of they have cancer developed because they consolidate their bad memories. Now, a gene has no importance unless it expresses and translates its relative proteins. That's why we have, next step, we have done proteomics analysis. And we had found out exactly that if a X gene is expressed, whether the gene-related protein is also overexpressed or not. And we have found out here 8 to 9,000 gene, and that's a 79 to 57 gene were only found overexpressed. So 90% of genes, we have no correlation with the genetics data. Means in epigenetics, genes were different, while proteomics proteins were different. That's why the correlation was very, very less, but we found a significant change on this. And most of the proteins which found significant, they control the mitochondrial energetics, energy metabolism, epigenetics, learning memory, and astrocytes. Most of the change in brain toxicity after radiation happened through astrogliosis. It's a basic process because glia are more important in maintaining the nutrition of the brain. They raise the energy for the neurons, and that's why the cognitive function happens. So what is the correlation between this? That's why we finally may make validate the regulatory correlation between epigenetics and proteomics data. Whether the gene is overexpressed and it's also the relative protein is overexpressed, out of 7,000, in the last slide we found out only 111 genes. And now we correlated after the proteomics, and we only found there are 4 genes after 20,000 genes and proteins. Their gene is also the gene is also changed and the proteins is also changed. And this only identifies the one CRCT1. CRCT1 is an energetics marker which basically controls the biogenesis on the brains. Second is a fat beat, is a fat acid binding proteins which basically control the fat metabolism brain, and that's why the one reason after cranial irradiations, most of the patients, the white matter toxicity has been observed. Because the demyelination of brain happens, 90% of the patients who go for cranial radiations, the demyelination is a problem of this decrease in the genes which control the fat metabolism and also the myelination formation. So further, epigenetics, transcriptomics and proteomics doesn't give any solid output. You have to reconfirm this data with the PCR or Western blotings. So we have further edited animals, and we found the gene which we found overexpressed in proteomics, also the transcriptomics, we did the Western analysis. We ordered the antibody, we designed basically to the vendors, and they had designed, and we found the same just like the genes. Whatever that we found, they are also overexpressed, but the quantity was completely different than epigenetics. Like epigenetics, they are saying 1-fold change, proteomics they are having 7-fold change, while the real scenario, they are saying almost 50% change or 45% change was there. But there was a correlation between proteomics and transcriptomics data. So next steps, we found the high the glycolysis, when there's a glucose enter in the brains, is go to the non-mitochondrial transformation, then it's into the mitochondria. And mitochondria, we are only focusing on the astrocytes. Because why astrocytes? Because astrocytes is a quick energy source for the neurons. Neurons directly takes the glucose, but it's astrocytes who converts pyruvate to the glucose very efficiently and maintain the glucose level in the brain. So we have identified all the enzymes who control cytosolic glycolysis, mitochondrial energetics, and glucose transporters. So what we have done, when the cranial radiation was given 9 gray, and we found a significantly decrease in the hexokinase, also their metabolites, not only the enzymes, because enzymes increase, decrease doesn't play vital roles. Unless its metabolites goes down, because end product goes down, then it has a validation. So we validated the both enzyme is also down, its metabolite is also down, and we had also done with the phosphofructokinase. This is also a key rate limiting steps on glycolysis, and both of the enzyme has gone down. Same we have seen in pyruvate. So we can see in the cranial radiation significantly impair the glycolytic enzymes. It may not be a key roles because the brain also has a subtle pathway where all this metabolism has another pathway. We're going to share it later for that. So now what we found, how the another mitochondrial enzyme pyruvate pyruvate dehydrogenase, lactate dehydrogenase. In this, we have not identified all this in the brain. We have identified, we have messed up the brains. Then we isolated only astrocytes, because almost the neuron has 50 trillion neurons. Brain has 50 trillion neurons. After that, 70% are the neuron, 30% are the astrocytes, 20% are the microglia. We have isolated the astrocytes from the brain. We have to filter it out, and then we have identified how this astrocytes brain is going down. And we have found it the same. Further, the other mechanisms we have find out, because if you see in most of the neurological disorders, the energy disturbance happens to the important cycles called glutamate-glutamine cycles. Even there's a law in the glutamase. Brain is very smart. He can overtake the glutamate from the blood pools and then make the glucose. And this is usually happening in most of the fasted conditions, and also the condition where the neuron, just like you are in fastings. So what will happen if the glutamine concentration goes down in the brain? That's why now glutamine has become a very important drug for the Alzheimer and Parkinsonians. If you inject the glutamine, it can be propagated. So what will happen? Glutamine, there is 3 mechanisms. Glutamine also can convert to glutamate. It can also convert to GABA. So what we have identified, first of all, in cranial radiations reduces the glutamine concentrations, and we have specially identified the hippocampus and prefrontal cortex. Why this part? Because these are the most sensitive cranial radiations. Once glutamine concentration goes down, then we found the GABA is going on, because GABA, so what will happen? GABA is going down it here. And second mechanism is also going on the glutamate, because glutamine concentration is going up. So means there's no change on glutamine. Conversion of glutamine to glutamate has been shifted. Brain became excitatory toxicity. So brain is also a balance, inhibitory neuron and excitatory neurons. So what will happen after radiations? The excitatory neuron are becoming more hypers. That's why the most of the neurodegenerations in cranial radiation happen by excitotoxicity, but glutamine toxicity is very prone to this. And this we have confirmed in the astrocytes. You can see the immunohistochemistry picture. In 0 gray, the green is basically the GFP cell, is a astrocytes, while this 9 gray is a glutamine synthetase, is an enzyme which synthesizes the glutamines. This enzyme goes down. So this cycle has been disturbed. So if the cycle has been disturbed, the disturbance of glutamate-glutamine cycle is happening. That's why we call one of the mechanism or this decrease. Second mechanism, if the glutamine is there, glucose is there, the radiation significantly kills the GLUT1 and GLUT3 is a transporter for the glucose. GLUT1 and GLUT3 are sodium independent, means they are only present on crucial part of brain. They are basically toll-free glucose. They are mostly present in blood-brain barrier. So blood-brain barrier are also in the neurons. Neuron doesn't need to pay anything to get energy, just like a heart. Heart can take glucose without any transporter. Same as the brain, blood-brain cannot take. What we have been observed here, this is a part of hippocampus, basically neurogenic region. This is called GCL, granular cell layer. This is most of the new cells are there. So what will happen in the green are the basically neurons, while the red are the glucose transporters. That significantly goes down on the after radiation. So what will happen? The glucose is not able to take the glucose. Even the diabetes, this condition is different. In diabetes, this condition is here, glucose transport has been goes down. So you can clearly see in this, even the glucose, even the neuron density is also going down. So this is glucose. Second part, we have determined the GLUT5. GLUT5 is selectively present on astrocytes. What's GLUT5 control? GLUT5 basically controls the formation of glucose on the microglia. So microglia and astrocytes, IBA1. Microglia are the basically brain phagocytic cells. They are also born on bone marrow, migrate to the brains, and they maintain a defense mechanism. Second, so this what will happen, so after going this GLUT5 is going down, and that's the reason most of the microglia are activated. 90% of the neurological disorders, Alzheimer, glucose, dementia, accelerated brain age, the microglia are basically deprived of glucose. And that's the one reason we have significantly found the GLUT5 goes down drastically on this, all this way. So that's the reason it is going. Second, we have also confirmed this not only immunohistochemistry, we have done Western, also the PCR, we have all these things done. So, conclusion of studies, we have found the transcriptomics and proteomics. Transcriptomics, we have identified nearly 4 genes where that completely correlates with the existing data. And we found the gene which basically controls the energetics on the neurons has critically play roles. functioning, the dysfunction of glycolysis, which is a critical part of any cell survivals. The glucokinase, hexokinase, phosphokinase goes down. They are critical roles and they are disturbed on the cranial radiations. Second, the glucose, we also have done the GLUT1 transporter. There are significant play roles on this. And other than we have done the behavior study, which I am not going to present here, but the animals who undergo cranial radiations, they are significantly deprived on the cognitive dysfunctions, where they saw impairment of learning and memories, where hippocampus and prefrontal cortex dependent. Thank you very much.
Thank you very much. In view of the time, we will move to the next presentation. So thank you very much. We go to the last presentation in this scientific session by Dr. Saxena from the Bhabha Atomic Research Center in Mumbai on evolution of international radiation dose limits recommendation from safety to precision.
Thank you very much for this opportunity. I am privileged to be a part of this August gathering and more privileged to be the last speaker of this August gathering. And being a last speaker, my condition is somewhat like Elizabeth Taylor's seventh husband. What more I can present now? So in fact, few speakers just before me, especially Mr. Perumal and Mr. Vivek, Dr. Vivek, they had covered a little part of what I'm going to speak. Nevertheless, I'll try my level best to speak a few words about how the international radiation dose limits recommendations evolved over a period of time. So, as we know that for the sake of convenience, we can classify the radiation dose limits among four kinds of categories. One, occupational, public, medical, and emergency. Fundamentally, there are two categories, occupational and public. And we have seen various applications of radiation, the nuclear fission in the past 3 days in the field of medical sciences, and Dr. Gautam had covered a very important field of use of radiation in food preservation. So we know the basically isotopes are used in these kinds of beneficial societally beneficial occupations. So these radionuclides and the isotopes are produced in the nuclear reactors, which could be of two types, research reactors or the nuclear power reactors. And nuclear power forms a very important part of the application of nuclear fission. And during the course of any profession which can give you kind of radiation, we call it occupational radiation. And a member of public which is receiving a dose not because of its profession but only because of its nearness to the facility is classified as public dose. Medical dose can be of three types. One, the occupational dose, which is as good as any occupation which is giving you radiation due to the profession. Or the second one is the dose given to the patient. And there is no limit because its benefits are immense. And the third one could be concurrent dose to the members of public who are in the waiting area, etc., which is very insignificant. And the fourth one is the emergency dose, that is for the purpose of radiological emergencies, where many workers, the police officers, the volunteers, they are working to rescue the people who can be affected due to the radiation leakage. As we see, the radiological protection is covered by radiation dose limits and a few principles which I am going to cover in the next slides, like justification on optimization. And we see the International Commission on Radiological Protection, somebody was talking about it and doubting its integrity. Nevertheless, these are the well-known apex bodies in the field of radiological protection, and they give
they have defined, you know, over a period of time, various limits for these 4 kinds of categories. Starting the ICRP started its working somewhere in 1926, and it came out with the first recommendation about the dose limits in 1934, where it was 500 millisievert per year for occupational worker. O denotes here occupational worker, and the P denotes the member of public, E denotes the emergency situation. 1950, it was further reduced to 150 millisievert per year for the occupational worker and 5 millisievert per year for the members of public. 1977 is still further, 50 millisievert from 150 to 50 millisievert per year for occupational and 1 millisievert per year for the members of public, which is still in vogue. But the occupational limit further was reduced in 1990 to 20 millisievert per year based on LNT model, which has been widely discussed over here, the linear non-threshold model. And the dose for the members of public remain same as was in during the ICRP 26, that was in 1977. And the basis of all these changes was the data which we had received from the epidemiological surveys and the survivors of nuclear bombs on Hiroshima and Nagasaki and the major accidents like Chernobyl. And in emergency situations also, in the life-saving operations, there is no radiation dose limit, but there are dose limits for the rescue operations, which can be situation specific. And this one thing which I have mentioned here as 2011, it pertains to particularly the Fukushima accident, where rescue operations for, rescuing the affected nearby population, the rescuers were allowed to go up to 250 millisieverts. So as I told previously also, the ICRP recommendations are based on 3 ethical principles of protection. First is the justification, where we state that no practice shall be adopted unless its introduction produces a positive net benefit to the members of society. So as we see, the medical applications or the power production, anything we have adopted and we have accepted has a net societal benefit. Optimization pertains to the all exposures shall be kept as low, this is known as ALARA principle, as reasonably achievable, economic and societal factors being taken into account, and the limitations of the technology are also considered into this. Dose limits, this is the part I'm going to cover. The doses to individuals shall not exceed the limits recommended for the appropriate circumstances by the Commission. And basically, dose limits purpose, as we'll see in the later slides, is to limit the probability of stochastic effects and to prevent the deterministic effects. I hope you all are aware about what are stochastic effects. These are the statistical effects which are fundamentally the cancer or hereditary effects, and the deterministic effects are the ones which are clinically manifested above a certain dose limit and for which there is a threshold. For stochastic effects, there is no threshold, and we consider they can start from the 0 dose level. So I have already spoken about the basis of change of radiation dose limits over a period of time, which we have seen is epidemiological data, nuclear bomb survivors data, and major nuclear accidents like Chernobyl. So now coming to the stochastic effects, which I told you, basically cancer and hereditary effects, we see that a zone up to a dose of 100 millisievert per annum, this is a zone which is very unpredictable and for which there is no certainty. As we move further in the dose levels, the risk factors increase with the increment of the dose level, and they are linearly proportional to the level of dose. This 100 millisievert, as Mr. Vivek has already covered, this is also masked by the natural background of radiation, which is typically 2.4 millisievert, the global average, but at certain areas, like he was talking about, even in the beaches of Kerala, it goes as high as 160 millisievert per annum. So these are the probabilistic stochastic effects and their variation with the dose levels. We have, somebody had asked at the end of Mr. Vivek's presentation about the possibility of reduction of dose limit for occupational workers from 20 millisievert to 10 millisievert, and there are many conspiracy theories against the apex bodies which are expressed in various fora. However, as of now, these are all debatable things, and there has been a certain basis for that, for that particularly. That particular figure of that particular figure of 20 millisievert, because it corresponds to a risk of 5% per sievert. That is an acceptable risk because it corresponds in any industry across the board, whether it's nuclear industry or any other industry. The acceptable risk generally is 10 raised to power minus 3, that is 1 fatality among 1,000 workers. So this is based, if we back calculate 20 millisievert per annum, then it corresponds to that 10 raised to power minus 3 probability of risk, and that too will happen after an age of 65 years, much after the working life of a worker. So we can see these are very conservative limits, and as I told you, the stochastic effects are based the limits for stochastic effects are based on epidemiological data because these are just probability based occurrences, whereas deterministic effects, where we see the clinically observable symptoms in a patient or in a victim, we are having clinical data, and we are having above a dose of 1 gray, there are clear symptoms in the patient starting with NVD syndrome, nausea, vomiting, and diarrhea syndrome. There could be any kind of thing like alopecia or the cataract or to say erythema, etc. So there is 100% certainty of some kind of detriment, some kind of clinically observable effect after a dose of 1 sievert. There are various risk estimation models which are used in the dose limitation concepts, and 2 of them very commonly used models are multiplication risk model and the additive risk model. And the multiplicative risk model considers excess risk as a multiple of the natural age-specific cancer risk. As we know, with the passage of age, the cancer risk also increase. These are more in the older population. And the multiplicative risk model, which is more conservative, assumes that these are the in the multiples of the natural occurrences with the age, whereas additive risk model considers a fixed, constant excess cancer rates above the normal natural cancers. This is the most debated part of any health physicist or radiologist, radiation-related worker, linear no threshold model, and which is the basis of present radiation protection. Here we see that this part is debatable. It could be supralinear. I mean, effects could be, detriments could be more, or the hormesis, where there could be beneficial effects of the low dose of radiations up to the dose of 100 millisievert. And this model is based on the exposure from the atomic bomb survivors data, which gives the linear no threshold LNT model. And we extrapolate it to LNT model, which states that there is no dose limit and it starts linearly from the dose of 0 millisievert. These are the different dose levels. As we see that LD5060 comes at around 3 to 6 millisievert, where there are 50% of deaths within a span of 2 months. During the emergency, we have to avert the large collective dose because large number of people are exposed to the radiation, and these rescue operations, they define certain limits. Like in order to avert a large collective dose, we are allowed up to 100 millisievert, but like I have told you initially that we went up to 250 millisievert. These are all situation specific actions to prevent severe deterministic effects. Because there is high dose level, we can go up to a dose of 500 millisievert. In life-saving actions, there are no dose limits. So dose limits purpose, I have already spoken about it, that we have to minimize the risk of radiation-induced effects, particularly the stochastic effects, and we have to prevent the deterministic effects. These are the dose limits for occupational exposures and public exposure. As we can see, the whole body exposure, the effective dose for the occupational workers per annum is 20 millisievert. We can go up to 50. Internationally, it's recommended that in a particular year, we can go up to 50 millisievert per year, given the average comes out to be 20 millisievert per year in a 5 years block. But our Indian agency, Atomic Energy Regulatory Board, being more conservative, we have limited it from 50 to 30 millisievert per annum. So we can go up to 30 millisievert per year in India maximum, given that we don't exceed this whole dose limit in 5 years averaging. Lengths for members of public, it remains 1 millisievert per year. There are equivalent dose for different body parts, which is for lens of eye and for skin. For occupational workers, it is 150 millisievert per annum, and for members of public, it's 50 millisievert per annum. These are examples of different radiation dose levels. For the interest of medical diagnosis purpose, we see there are different kinds of radiation doses which are given to the patient. It is not pertaining to the occupational dose which is received by the doctor or the medical practitioner during the course of administration of this procedure. So we can see the PET scan and X-ray CT scan, they give the maximum dose in general, and dental imaging gives the minimal dose. This was the basis of that 5% per sievert detriment that was considered for the risk estimation and for the establishment of the dose limits. So an average of 6 and 4 comes to be 5. So we consider 5% per sievert per annum. If it is given to 100 people, then there could be a possibility of likelihood of 5 deaths. And that is the basis of 20 millisievert per annum for the occupational workers. So my time is coming to an end. I'll just like to wrap it up. In the end, I can just say that dose criteria for emergency worker, there is no dose limit. And as the situation demands, for the rescue and for the collective dose aversion, we can go to a very high level also, up to 500 millisievert. Thank you so much.
Thank you very much, Dr. Saxena. Thank you very much. So we almost complete this session, and I hand over it to the person who is steering the proceedings.
Thank you, sir, for sharing your valuable insights. Now, we would like to request Dr. J.K. Singh, Director, Sri Sai Institute of Medical Sciences, to felicitate Professor Sang Ji Ko, Atomic Corp from Republic of Korea. Chairpersons, please kindly join.
Now we have come to the end of this scientific session. After that, now we are going to give the award. There are three types of award: Young Scientist Award, another is the Poster Presentation Award, and some Oral Presentation Award. 5 in each category. So after award session, I will call one by one, and after each category of award, then we'll go for a validatory function of it, hardly 10 minutes. And then the lunch is ready. Everybody will go and take the lunch. Thank you.
We would like to ask Dr. Amit Kumar to announce the name, call upon the names.
Yeah, on behalf of the organizers and in association with the Society for Radiation Research, we are going to complete this important and encouraging ceremony, that is the declaration of awards in 3 different categories. So we are going to begin with this. There are total 4 categories of awards. First one is Young Scientist Award, second is Oral Presentation Award, third is Poster Presentation Award, and fourth is Special Appreciation Award category. So in the first category, to present the award, I would like to request our honorary Dr. Iliakis. Dr. Iliakis, please join us. Please join the Dr. J.K. Singh and Dr. K.P. Mishra, the founder president, SRR, Dr. J.K. Singh, organizing secretary, ICRR HE 2024, and also Dr. Anita Kumari from the Nalanda Institute, Patna. Yes. Now I'm going to declare the name of these awardees, which are equal within that category. So for Young Scientist Award, the first candidate is Venki Desh Babu Senthil. Please come. Please be very fast so that we will save the time to begin the valedictory function. Saurav Kumar Das, Shishukant Shuman, Niharika Nima Baijan, and Sachidanand Behra. Please come. Please come. And I would request Dr. Iliakis to, please come in the group. Please come. Please all come. Yes. So that we will have a group photo of all the awardees. Yes, please. Please come. Yes, all 5 people. Yes. Now I request Dr. Iliakis to present the certificate and the prize. Dr. Iliakis, to all the winners of the Young Scientist Award, SRR Young Scientist Award. Yes. 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 To Saurav Kumar Das and Shishukant Suman. Now next is Saurav Kumar Das. Yes, it's indeed an honor to. It's a very encouraging movement for these young radiation researchers. I hope it will inspire them to expand their R&D activities in India and abroad. And next is Niharika. Please come forward. Niharika, yes. Yes. And the next. Next is Sachidanand Behra. We all have. Yes, please come. Yeah. Oh, thank you. And now I would request all the awardees that you please come forward so that we will all have the group photo, and please display your certificate. Yeah, now we move on to the next category of award, that's Oral Presentation Award. And so the winners are Jubilee Purkayastha. Please come forward. Suchi Bhagi. Yes, you are there, right. Please come. Ishan Gunjal. For award you should run fast, otherwise somebody will take away. Please come. I used to run, from the first, from the top steps to on the stage. So please come. You should be excited to receive this award. Basumati Rajan. Yes. You need not to run, please. Somebody is there to take care. Please come. So I repeat the names: Jubilee, Suchi Bhagi, Ishan Gunjal, and Ajas Kasata Datta, and Basumati Rajan. I hope all 5 are present. If anybody is absent, it can be received on behalf of the absent candidate. Yes, please. Yeah. Yes, and yes, Dr. Mishra, please hand over the. Next is Vasumati. Yes, Vasumati Rajan. Yes, please join. And okay, all 5 completed. Yes. You want here? Okay. So it's an important announcement. Out of 5, 2 oral presentation awardees are not present in the auditorium. This is Jubilee and Ishan Gunjal. So we will hand over it. We will take care the transfer of these awards and its announcement. Now, next we move to the poster presentation award, and the winners of the poster presentation award is Dr. Tanmay Roy. Please come and stand here. Dr. Maria Rose Joseph, Dr. Niyati Dhingra, Dr. Ambika Shandi Daj, and Dr. Shikha Shiri. Please come, all 5, and I would request Dr. J.K. Singh to present the poster to present the award to our poster award winners. Yes, please come. First, Dr. Tanmay Roy. Yes. Tanmay. Dr. Maria Rose. Yes. Dr. Niyati Dhingra. Yes. And Dr. Ambika Shandiyal. And Dr. Shikha Shiri. Yes, Dr. Dr. Shikha Shri, yes. And then I request all 5 awardees that we will have a group photo. Yeah. Dr. Maria Rose. Yes. Thank you. Yes, Gopi, please. Shikha Shri, yeah. Oh, you are from Inmas, yeah. Yes. Yes. Now I request all 5 awardees to, yeah. Shikha Shri, yes, yes, please move on. Great. Shikha Shri, sir. Singh, sir, please, yeah. Shikha Shri, yes. Yeah. Please have a group photo of all 5 awardees, right? In between. Yeah. एक group photo ले लीजिए, है ना? Yes. Please take. This is the last category of the award. This is Special Appreciation Award, and this award goes to Mr. Sudhakar Pandey, who has contributed for the development of our SRR video. So it's very nice, and I think on behalf of him, I would request Dr. Pandey, Dr. B.N. Pandey, to receive his award. And second is Dr. Deepak Nayak, Baritone Solution, Mumbai. Mr. Deepak Nayak has been helping us in development of the website, so SRR website and the website for hosting the conference things. Yes. So I would request Dr. J.K. Singh to present the certificate and award to Dr. B.N. Pandey on their behalf. Yes. Yes. So for Mr. Sudhakar Pandey, and also for Mr. Deepak Nayak, for both. Yeah. So thank you very much all the awardees for your presence, especially just before valedictory function. And second, I also thank yeah. Thank you, Dr. Ilyakis, Dr. K.P. Mishra, and Dr. J.K. Singh to shower your blessings in the form of these awards to our young and next generation of radiation researchers in India. And now we move on to our valedictory function, and then after that we are just, we know that we want to have the lunch. So after, I hand over it to the real steer persons, actually, who will, yes, so we are going to valedictory function? Yes. We are going to begin the valedictory functions, so I would request the hall management people to please arrange the dash, and then.
Where is Dr. Amit? Secretary of the association. Oh, Amit, yes, please come. You can call everyone, because I don't have.
Everyone. As we gather here for the valedictory function of the International Conference on Radiation Research, Impact on Human Health and Environment, it is time to reflect on the success of this event and celebrate the fruitful discussions, collaborations, and knowledge sharing that have taken place over the past 3 days. This conference has been a journey of innovation and inspiration, and it is only fitting that we conclude it by acknowledging the efforts of everyone who made it possible and setting the stage for future advancements. Let us begin this valedictory function by inviting Dr. J.K. Singh, Organizing Chairman, Dr. K.P. Mishra, Founder President of SRR, Dr. George Iliakis, President IARR, Dr. B.N. Pandey, Vice President SARR, Dr. Amit Kumar, Secretary SRR, and Dr. Anita Kumari, Treasurer SRR, to be on the dais. Dr. P.N. Pandey, please join us in the dais. Now I would like to call upon Dr. J.K. Singh, Organizing Chairman, to share a few thoughts.
I was just talking to Dr. Mishra that every time I go and attend the various types of conferences in India and outside India, but I've never attended 4 days conference in one stretch. Actually, from the day one also, every program was made so much interesting, and scientifically it is so much enriching that everybody, even of the last time of the day, they were sitting here. And everybody, I think, not only the delegates, but the persons who are attending in Patna in the radiation oncology department, they are very much benefited, and particularly the PG student and the students has also been very much benefited, and it was a very, very fruitful lectures. And I think many persons, almost 18 in numbers, they come from the foreign countries to participate in this particular conference, and after crossing a long way, they are long way from different countries, they are here, and they share their views with us, for everybody. Bihar is always known for its hospitality. Nobody bothers about the pick up and drop and cares for they only provide you the scientific content, that's all, wherever you go to the foreign countries. Here we have done everybody has been taken care of, right from the pick up, drop, transportation, and you know what is the interesting? Even Dr. Mishra has not taken the breakfast. The message come to me. He has not taken the breakfast. We are so much particular for everyone that we care throughout the course of this particular. Apart from that, the scientific content was made by Dr. Pandey, very much genius, versatile, and the visionary person, and very much having the great organizing capacity also. So day and night he was guiding us. Everything has been done by him only. We are just doing the, suppose anybody plans and the execution is done by the persons. We are the executing body only. So whatever the credit of this conference goes to one person, that is Dr. Pandey. Give him a gift. And I'm very much thankful to everyone. I know that there are many shortcomings in any conference, and this conference has also many shortcomings. So please be here with us. We have very less time, and Patna, there is marriage season, and many marriages are going on. So the traffic, you must be seeing, it's very high. And because after 14th December, there is no auspicious day. So they do the marriage ceremony before that. So many marriage ceremonies are going on. Even in the hotel they were residing. I wanted to take you personally to the most of the places, and that is worth seeing places in or around Patna. But I could not get time, and Dr. Pandey has made us so much busy, and that daytime you cannot go, we cannot think of going outside. So I will invite you, whenever you come next time, just keep one day with you, and there are so many interesting places. I know most of the religions has a deep roots in the Bihar. All the religions, Sikhism, Buddhism, Jainism, Hinduism, all the, and there are many historical places, interesting places. You'll be thrilled to see those places, and having historical importance. So next time, whenever you come to Bihar, come to Patna, just give me a phone call. I will arrange for everyone to go and see the worth seeing places in and around Patna. So thank you once again for coming, visiting, and spending a valuable time of yours with us. Thank you.
Thank you, sir. Now I would like to call upon Dr. K.P. Mishra to share a few words.
I know valedictory function is delaying the lunch, so we will finish in just short words that the way Dr. Singh and his team, Anita ji and many others, organized this conference, we have been overwhelmed. And I must say the kind of hospitality, the kind of transportation, our needs and take care minute to minute, lunch, breakfast, everything has been excellent. I cannot imagine anything better than this. So that's my appreciation of the whole local organizing committee. Please give big hand to them to be feeling that this is the way they should work. Let me also say, I expect them to work this way. So they should continue doing this and try to do better next time when we come to Patna. And from the point of view of society, I would like to congratulate all those who got Young Scientist Award, Poster Award, Appreciation Award, all kinds of things. We are ready to help all young people to come to level and to assist you, to motivate you, and also that's why we have here Charles Iliakis, the President of International Association of Radiation Research. We are very fortunate that he has given this much time. So I'd like to appreciate efforts of all, especially all you participants. And we would like to end just by saying again that we hope to meet again in even another place, another gathering, another motivation, maybe another environment. So, and we have, the society has planned all up to 2030 activities. So we look forward to your participation in future. I would like to just say one word about Dr. Pandey and Dr. Amit Kumar. You know, as their mentor, when I see them performing better and better, every time I am on the stage, every time I see them talking, I feel proud. And I would like to this place on record of my appreciation from my heart. Some of the young people who gave talk, the Nina, very nice talk, Prabodh Kumar, I couldn't believe that he is the same boy who was my student. He's talking like a big professor and talking like very confidence. So that's exactly what the society aims. So as a senior person in the team, I have all admiration and all my gratefulness and satisfaction of such a wonderful teamwork that has been going on in the society. So again, my appreciation to Professor Singh, Dr. Anitaji, all of the team members who are not present here, and we are very amazed to see that such a reception, such a care, and such a hospitality has been arranged. Everything from A to Z. I have no any place where any comments can come. So Dr. Singh, I would like to personally appreciate your efforts very much. And thank you very much, ladies and gentlemen.
Thank you, sir, for your kind words. That means a lot to us. Now I request Dr. George Eliakas to share a few words.
Well, I will also say that it has been a great pleasure for me to be here. I enjoy every minute of it. I enjoy seeing you again, everyone. And I really cherish the opportunity that you are giving me by inviting me again and again. I would like to personally thank Dr. Mishra for initiating this many years ago, but Dr. Panda and Dr. Kumar for helping me in every way they could. But of course, the greatest thank go to the local organizers who made everything here possible, and the more I stay, the more I realize how much help I'm getting, so I'm start having second thoughts about leaving. But anyway, it has been a great pleasure for me to be here. Again, thank you very much indeed, and keep on doing it, and stay persistent, and go, as Dr. Mishra also said, from the very good to the very best. And good luck from me to all of you.
Thank you, sir. Now I would like to ask Professor Dr. B.N. Pandey to share a few words.
So if I have to say in few words, maybe I cannot complete, but I remember like when I met last time to Dr. Singh in Bangalore in one of the meeting, and it was first meeting with him, and his personality was so impressive that I got attracted, and then after discussion we thought to let us have this meeting in Patna. So, and after that we have been begin, and I must tell that we have been discussing, and he is a good leader and guiding like what to do, and so we have been helping him to whatever best way we can do from Patna. And we have been disturbing him, sir, you many times at night and evening and morning, and I call many times at 8:30 when I reach to the office for some urgent things. I call him, and maybe that time he will be taking breakfast, and so I've been bothering him. And one most important person who I bothered during whole course of time, Dr. Behra. Always we have been discussing, and many times we have to, and after coming here I found that so many other team people like they have been working, and really appreciate their work. Dr. Anita, Dr. Pitanjali, and whole, I don't know the name of the people, but really it is our bottom of heart, it is appreciation to all of them, and let us give a big applause to whole team on behalf of society and my personal behalf. And I must say that if there may be some coming in terms of some scientific problem, I take my responsibility, and it is fault of my side if you find something, but I always urge to all of you, as a growing society, you do feel don't hesitate to write us your negative comments. We are not the people who accept only the positive only. If you find that somewhere some liking, some of them we appreciate, we know also that where we missed some of the points, but still if you find something that we need to improve, feel free to write to us on society email, and we will be trying to improve in next events. So it is a sort of a continuous growing. So I request all the faculty from India and abroad and students, and we are trying to make it so with these few words. And lastly, I like to thank all the delegates, students and foreign delegates for giving time. So with this, I really enjoyed the event, and let us hope you meet again in this SRR activity. Thank you very much.
Thank you, sir. Now I would like to all Dr. Amit Kumar to share words.
Yeah, thank you, Jenny, for giving me a few minutes. Yes, so as a secretary for Society for Radiation Research, my heart is indebted to Dr. J.K. Singh, who is the real architect for organizing this event at Patna. And the sub-architect is the Dr. B.N. Pandey. So as a secretary, I express my sincere thanks to both Dr. J.K. Singh, Dr. B.N. Pandey, and also the team that both of them have trained us. The members of the local organizing committee, and I can see my brain is just instillating their names, but I do not want to specify their names, but of course their contributions are quite visible. The whole local organizing committee from SSIMS and from Aiims Patna. And I have one thought to share, that as a organizing secretary and as a clinician in Patna, it's not just easy task to hold such a big international event. And we know the pains, we know the experiences, we know the feelings, we know the vibrations of your heart. We are not going to leave it. We will carry in our heart, and we will continue our interaction, which is not interaction, which is now a social bonds with Dr. J.K. Singh. We will continue with that, and we will try to return in every possible scientific aspects to you and your colleagues, which will help you in development of the radiation research in future. My second thanks, sincere gratitude, goes to all our esteemed overseas speakers who have took all the pain to travel. I mean, I know it's a kind of service to grow the radiation research community in India. Your deliberations in the form of great presentations, discussions, interactions, blessings, you are actually training the Indian research students that how to grow yourself into a good radiation research scientist. That's what matters. So I mean, the whole as Society for Radiation Research, senior members and myself, we are indebted to you also, to all overseas speakers. Thank you so much that you are traveling at every second year, and just enlightening us, just blessing us that this is how the science, this radiation science. And I also see the great engagement from India, engagement of young radiation research students, young growing radiation faculties, who are now very well connected to our overseas guests. So that this network, these collaborative interactions, or these interactions will get transformed, I hope, into very fruitful collaborative interactions, which will help again in the development of radiation research. I hope I am not taking too much of time, because my co-partner, Dr. Anita Kumari, would also, because she also deserves to express the feelings in the form of vote of thanks, vote of gratitude to all of us. Yeah.
Now I request.
Yes, I request Jenny to.
Yeah. Now I request Dr. Anita Kumari to give a vote of thanks.
to one and all present here in this beautiful gathering. It's my honor and privilege to stand before you to deliver the vote of thanks for the International Conference on the Radiation Research, Impact on Human Health and Environment, held in conjunction with the 4th biennial meeting of the Society for Radiation Research. This remarkable event, hosted from the November 22nd to 24th at the prestigious All India Institute of Medical Science, Patna, Bihar, has been a testament to the power of collaboration, innovation, and academic excellence. It's jointly organized by Aiims Patna and Sri Sai Institute of Medical Sciences, Hajipur, under the esteemed aegis of Society for Radiation Research, India. This conference has brought together brilliant minds from across the globe to explore and discuss the profound impact of radiation research on human health and the environment. As we reflect on the wealth of knowledge, exchanged and meaningful connection forged during these 3 days, I would like to take this opportunity to express our deepest gratitude to everyone who made this conference a grand success. So my extended token of appreciation and gratitude to all the speakers, chairperson, and dignitaries for their mind-evolving talks and presentation. My sincere thanks goes to the founder, president, and editor-in-chief, Dr. K.P. Misra sir, president of this SRR, Dr. R. Bilimiga sir, who is not present here at this moment, our secretary, Dr. Amit Kumar, treasurer, Dr. Chandan Kumar, and of course, the Pandey sir, and Dr. Ilaski, to be here and giving so much time here. And I am thankful to all the staff members who helped in the successful organization of this international conference. My special thanks goes to the press media who have taken their initiative to spread the awareness among the countries in Bihar and all over the India. Also to all the medical representation who gave their extra effort to make this event successful. And last, all those who present here in this hall at this time. Thank you all.
Thank you, ma'am. Now I would like to call upon Dr. Amit Kumar for further proceedings.
Thank you, Jenny. So, just hardly 3-4 more minutes. As you all know that we have a tradition in our society that we invite our guests to have their observations about their experience during the conference and also the experience about all the event. In this, for this tradition, I would like to invite Dr. Kries, Professor Hans Kries from Amsterdam, the Netherlands. You please, to say a few words about your experience. Thank you very much for coming.
Yes, it's a pleasure to say a few words about my feelings attending this meeting. I've been coming to meetings on this subject for quite a number of years already, and at all occasions the let's say the hospitality and also the ability to organize a meeting was striking. At this meeting, what was really for me very good to see is that I saw quite a high level of the contributions, and that resulted of course also in very good discussions, but sometimes also resulted in some delays in the program, but after all we are here for this exchange of thoughts. So that part was already quite good. And I also saw a number of
innovations introduced, for instance, to have these flash poster presentations, where I could also see that after initially some people getting having to get accustomed to that, then during the meeting you could already see that it started to work and that it made people more enthusiastic and also better able to present their work, and that's also very good for the learning process of the PhD students present here. So in all, I felt that this was a very good experience. I have to make my compliments to the organizing committee and all of the other people involved in organizing this meeting, that this was such a good experience. So yes, it's my pleasure to be able to say this. Thank you very much.
Thank you, Professor Chris, for your kind sharing. May I invite Dr. Sophie Dobias from University of Munich, Germany, to please share your experience, your observations about this conference. Please come forward. Yeah. I think Dr. Sophie, for Dr. Sophie, it was the first time experience, right, for our ICRR conferences, but we have been interacting, so yes, please.
Yeah, thank you very much. So it was a really great honor for me to be here. So indeed, it was my first Asian conference on radiation research, and I really appreciate everything about it. So the food, the nice people, and the conversations, and to learn something about the culture, the Indian traditional culture, that was really, really interesting. And today I had the opportunity to have a look on the Department of Radiation Oncology here at Aiims Center, so that was really impressive as well. So thank you very much for everything.
Yes. Now I invite our invited speakers from INMAS, Dr. Damodar Gupta. Please express your feelings. You are our very respected guest, respected invited speakers from INMAS. Please.
Namaskar. Like always, the conference is organized very well. The best thing that I could identify or find out, the participation of a student and their encouragement was done really nicely. They were preferred and they were asked to present their work instead of sharing the data of all the senior colleagues or researchers. So it was really, in my view, it is one of the best motivation for the students and beginners who are going to contribute in science or radiation science in coming time. And very well organized. I would like to congratulate JK sir for really doing very, very good and well organized and really good hospitality over here. Thank you so much. Congratulations again.
Thank you, Dr. Damodar Gupta. Thank you very much to express your views. Now I would like to invite Dr. Nils Cordes from Dresden. He is the director, Oncure Center, Dresden, Germany. He was there with us during 5th ACRR in Mumbai. So please express, you can be very frank, I know that. Yeah.
Yes, thank you, Amit. Thank you, everybody, distinguished colleagues. So, yeah, it was again, after my first experience with you in Mumbai, it was again an extraordinary experience, and I'd like to thank Dr. Singh and his team and everybody who contributed to this wonderful conference and make it again very fruitful, and I met new people, and so I see that everybody is very dedicated and motivated to to pursue research, particularly in the field of radiation biology, which is very, very important, as everybody knows here. So Thank you very much, and would be a pleasure to come again. So thank you. Thank you to everybody. Yeah.
Yeah, I hope you are enjoying our spice in food and everything, our culture, and the very informal way we interact as a, our culture, part of the culture. Yes. Okay. Yeah, there is a positive input. I would like to invite Professor Sung Ki Zo. With lot of struggle, there was some during his travel, there was some delay in some things, and then but Professor Zo at this age, he did not compromise with his commitment towards our society and ICRR. With full respect, Dr. Zo, please share your views. You are very close to us. Yes.
Thank you very much for all members, all committee members. And it's a great honor for me to hear and to present my research data. And especially thanks to Dr. Misra. Every time he showed me the warm hospitality, and especially Dr. PJ Singh, also he carefully helped me. And so it's a very great conference, and congratulations. And I hope that this conference and this association will be bigger and bigger, warmer and warmer. Okay, thank you everybody.
We have a very senior person from Hajipur, and he delivered the invited talk at he's from Naipur, Dr. Parihar, Dr. Vaipan Kumar Parihar. Please come.
Bipan Parihar.
Yeah, oh, so it's
Once again, thank you very much for inviting this podium. I think this is my first meeting this, though I was very long associated with radiation oncology and so the radiation physics back to my PhD. A long time back, I was with Dr. Uma Devi, Dr. Jagatiya, and Dr. Satish Rao. I was in Manipal. Then I went to the US, almost for 15 years there in the, George was very well known that we discussed a long lot between the George. And he was with like my boss, George Charles Limoli, Frank Cucineta. He was a NASA director at that time. So I worked with them. Then he finally recognized me. I was there. So pretty much I will be more involved in this, and I will be very active after that. And we instantly started. But I'm very fantastic to see the great research and great students' motivations. And the selection of I have no doubt on Dr. J.K. Singh. We are already working a lot of collaborations. Dr. J.K. Singh has a 2 hospital, SS hospital. Now I forgot to present my last acknowledgement slides. Dr. J.K. Singh has established a lot of center for the clinical trials, also the basic research on the radiation oncology. And fantastic mechanisms, and we hope we will grow this community. I am going to put more NIPER students from the radiation research. So we will going to make a better platform, and for NIPER side also. Some faculty are also working on the radiation research. So thank you very much for this invitation.
Thank you very much. And Dr. I would like, in this series, it's important that we have the views of some young growing faculty. Dr. and in that, Dr. Prabodh Mehra. Prabodh Mehra? Yeah, please. Prabodh Mehra, please come. He's working with Professor Andres Wojcik. And it's a very senior scientist. And before that, he has worked with Professor Iliakis. So your views are very important. Yeah, please come.
Wow, thank you so much. It's a pleasure to give my own experience. This conference, I would say, it's a very, very nice platform, and as the Society for Radiation Research, it says, a platform for radiation researchers. I will buy it 100%. It's a really platform for radiation researchers. And I started my journey from this society's first conference in 2016. Then I met with George Iliakis in 2017. I interacted with him. So that is how I made connections with everyone, and I learned a lot of things from this platform. So it's a really good platform, and I am so happy that Dr. J.K. Singh organized this conference in Patna, which is a very historical place, and it gave me an opportunity to come here, and the hospitality, wow, it's really nice. Everyone, I haven't seen anyone in a stressed face whenever I asked something. Everyone was quite happy to answer in their best possible way, especially some of the foods that I was wondering to go outside to taste. It was available here, like litti chokha. So I was really impressed with that kind of arrangement, and the food was also very delicious. So I would say it was a very nice thing and a nice success of this conference. And one more thing I would tell to everyone, that Society for Radiation Research is also in the social media platforms. However, you are talking about Facebook, Instagram, Twitter, it is there, and it is again soon coming on LinkedIn as well. So please follow the societies in the social media, and let's make a really nice family. Thank you so much, everyone. Thank you.
We are just completing this tradition, and I actually used to invite some students to express their experience. And may I invite Dr. Niharika. Niharika, would you please share your views, that how did you feel about this conference? Because I know you have been experiencing many conferences. So yeah, let's have your views. Yeah.
Thank you so much, sir, for asking me for this. It was a wonderful experience to talk it out over here, to explain my research. It was my first such presentation, and as such, it's just my second conference. But yeah, I really liked the experience, and interacting with so many people over here was a delightful moment and enriching for me as well. Thank you so much.
Yeah. And now it's an open call. If anybody would like to please say anything, please come forward and just share any suggestion or anything. Dr. Himansi, would you like? Yes, you please, if you want, you please come. Okay? Is okay, fine. Okay, so now we complete this, and thank you very much for all the senior and students, senior people and students, to share your views, your feelings. Now I move on to the just last part, and with all respect, I invite Dr. J.K. Singh to announce the closer. Yeah, thank you, Organizing Secretary Dr. J.K. Singh, ICRRE 2024. Please, sir, please come.
No. Now we come to the end of all the sessions, scientific sessions, and every session award winning, everything. So with this, we conclude this entire conference, and I think you all are going with the sweet memories of Patna, and I think we should meet again anytime after, might be 3-4 years or 5 years, we should meet again, and that time we will give you again a most warm welcome, which I could not give this time. So thank you everyone for coming, participating, and spending so much time with us. Thank you. So we conclude this session.
Thank you, sir. Now I request everyone to come up on stage for a group photo. Everyone, please, on the stage.